So, welcome everybody. We're going to kick things off in a minute or so, so if folks want to take a seat, we can get started. So welcome to Nextflow Summit in Boston. This is our first time doing this event in North America. Very excited to do so. A little history on the event. And thanks to you folks for tuning up and for making it the event that it's going to be. We've already had some period, obviously, with the hackathon so far, but for the next day and a half or so, we're going to hopefully a ton of exciting talks all around Nextflow and the Nextflow ecosystem. A little bit of history on the event. This started off in really around 2017, where we did our first hackathon, which is called NF Hack. The project was much smaller at the time. The project, in terms of Nextflow, kicked off in 2013 at the Center of Genomic Regulation. We were looking at multiple sequence alignment. As it's kind of continued to grow, we were sitting there looking at the traffic of Nextflow and thinking, what's happening here? All of a sudden, the top of this graph in Google Analytics was this place called Massachusetts. And it was kind of this weird thing, completely accidental. So it's really nice to be here finally to run an event, given the kind of interest which has happened from that as well. So a little bit of kicking off a little history here. So when I mentioned that first hackathon event, that happened around 2017. You can see that at the time, Nextflow really had some interest, but it was relatively low. And since then, it's just really been organic growth, which has been driving the project forward. And I talk a lot. We were originally obviously based in Barcelona, where we started the project. The company Sarek was founded there. But really, since then, if we look at where the user base is, where the customers are, it's really driven from a significant interest in the US, and in particular in the Boston area, and also in California, where the kind of biotechs are focused as well. So jumping on to this, when we kind of look at that and we look at that user base, there's nothing really specific in Nextflow that says this should be used for biopharma or this should be used for life sciences. But I guess one of the key things is kind of looking at what the applications people are developing on top of Nextflow. And when we look at that kind of breakdown, I've kind of gone through a little bit of the audience of the people who are here today and looking at the kind of really amazing science that folks are doing here. Whether this is across biopharma and medicine in terms of this target identification with CRISPR screens, we're looking at streamlining drug approval with RNA-seq. Really, the list continues, a broad range of applications, and really people are coming to Nextflow to solve many of those problems that they have. Biopharma is obviously the largest use case of this, but we also see it in agriculture and animal health, in synthetic biology, really any areas where there's large amounts of sequencing, and that sequencing is typically tied to some outcome, which maybe is a clinical trial, or maybe this is related to the development of some new materials, really driving a lot of the adoption of Nextflow. And we also see it outside of the life sciences space as well. We've spent some time looking at some pipelines recently in terms of sort of radio astronomy as well as like satellite image analysis. So there's some really interesting applications of Nextflow which are happening. And so I really encourage you over the next day and a half or so to mix and to mingle, to learn about the science that colleagues and the like are doing, and to kind of learn from that and to continue to collaborate. On to a few logistics. So there's Wi-Fi, which is in the building. You should be able to connect to this via the Hilton Honors meeting, and there is the password for that, which is Patriots. If you see any of the folks with the white Nextflow Summit t-shirts on, you can ask them as well for anything like this. We've got Phil at the very back there. You can wave to Phil. And related to that, there's going to be a Slack channel which is open, which is called Summit 2023 in Boston. And this channel is where all of the speaker notes are going to be taking place. So if you've got questions for speakers, you can post them then. If you want to interact with other folks who are around, want to find people to connect with, you can use those channels and those ways to do that. On to the talks themselves. So as I mentioned before, you can write those questions into that channel. Really great if folks can upvote their questions as well. So as speakers are speaking, then the moderators can use that information to ask those questions, as well as kind of follow up with folks afterwards. So if there's any questions that you would like to see answered, which are not answered, you can follow up with those, and again, would ask the speakers to do the same on that. With regards to streaming, we have this live streamed on YouTube, and they'll also be recorded and edited and posted afterwards, so folks can follow up. If you want to share particular interesting talks with your colleagues, feel free to do so on that. Now for a little change of tact, you may remember this logo from a little while ago now. It feels like a long time ago, but it was literally like a month. The last month or so, we've been doing a little bit of a rebranding project. As part of that, we've been transitioning from the original Nextflow logo to our new rendition of this, which is, you can see here. Obviously, there's a lot of similarities of that. And part of the reason for this was to really create some cohesiveness around the brand that we've been building with Nextflow and with Sarek as well. How it started, we began as an academic project, usually a project that we put onto GitHub. Since then, we started to get some users. We created a company, then we created a commercial product. It was a little bit like a backwards way to do things, and now we've been taking the time to really reassess that, to consider exactly what's important to us and how we can link all of that, those things together in a cohesive way. It took a bit of soul searching, to be honest, to kind of thinking about what was the essence of Nextflow and what was that. For us, it was kind of thinking about how we can apply modern software engineering practices, how we can make it easy for people to collaborate in science via use of cloud, containers, source code management with Git. Bring all of that together for workflows, and that's essentially what Nextflow is. When we think about that more broadly, though, what about outside of Nextflows? And really kind of thought about that purpose there, which is for us to make scientific data analysis accessible at any scale. And this is kind of a key thing which drives us now across not just workflows, but those other areas as well. If we look about the mission, it's to empower scientists with modern software engineering. So really to give folks that modern software engineering toolkit to be able to build on top of. And then kind of finally onto that is, what are we developing here? Well, it's not just like a single platform here or a single tool in some case. It's really a stack. And the idea is here we're kind of using biotech in a broad sense, but how can we really give folks all of the software and make that software accessible, make the data accessible, make the infrastructure collaborative in a way to build out that in that area. So this is our new branding, which we kicked off about a month ago or so. And you can see here it's really split now across not just Nextflow, but into multi-QC. It's a very widely used reporting tool. Fusion, which is our cloud-native file system, as well as Wave for container provisioning. And all of these tools really come together to play in this ecosystem, which is also joined and combined with many other pieces of software and tools and resources to make them available. As part of that rebranding, there's also a new brand name for what we previously called Nextflow Tower. And this has simply been rebranded to Sarek to make things simple. When we want to be specific about that, we often talk about the Sarek platform, but it's really the concept of bringing all of that together into the piece. And I'll be speaking a fair bit more on that in my talk tomorrow, really looking at a little bit of the usage of that and the technology there. So back to our agenda for the next day and a half or so. You can see we've already had a fantastic hackathon session, and today we're going to be kicking off with a couple of sessions which will be finishing. We're going to have a reception afterwards, which will be here, followed by the talks which will be taking place tomorrow. I'd point out there's also a sunrise run and walk, which will be taking place tomorrow at 7 a.m. for people who are keen. I would suggest wrapping up warm, particularly if you're not from the area as well. And with that, I'd just like to thank all of our wonderful sponsors. It's really great to get so many people and sort of building as part of this ecosystem. And I will pass it over to our first speaker. Let's have a lot of fun. Should be good.
All right. Good afternoon, everybody. So, let's start with my first naive take. Fairly young guy here. So, I'm neither a data engineer nor a data scientist, but I just wanted to draw some parallels here between the two and kind of define them here so we're all working on the same definition. Oops. So, data engineers, typically when you say data engineering, you think ETL, which is extract, transform, and load. And then data engineers typically work with databases. They focus on data quality, and they work on building pipelines for the data scientists and an emphasis on getting the data into formats that they can use. And then data scientists, on the other hand, use statistics, create models, machine learning in parentheses. They work on creating reports from those. It's not necessarily that people are one or the other. They can be both at the same time. It's more so putting the work that you're doing into separate buckets. So my second naive take here, maybe a little controversial. Bioinformatics and computational biology. Bioinformatics, you focus on running tools. We work with files, focus on data quality. Focus is on building pipelines that transform the data into formats that then computational biologists can use. So computational biologists focus on the stats. They create models, focus on creating reports, create algorithms. Again, you're neither one or the other. You can be both. It's great. But just kind of wanted to draw the parallels between the two before we dove into all of this and where I kind of see the fields myself. So, big data. It's dead. The modern data struggle here that we've kind of created is very few people are making these ginormous queries. They're not, that's what they found at BigQuery, was they had tons and tons of, I guess I'll keep going. So they kept making a ton of queries, and they found what actually people were doing was they were actually just using BigQuery because it was so easy to use, not because they needed to query petabytes of data and do these massive queries. Most of it's actually done on recent data. Think about when you're running a sequencing facility, you're mostly processing the data that has just come off the sequencer, not working through all of these like back samples in that sense and reprocessing those. And a lot of people save it for a really long time. Like, what if we need it in the future though? What if we need to reprocess these? That's fine, we put it in Glacier and move on with our lives. And then, so now all these files are sitting in object stores, like S3, for example, as well. And as bioinformaticians, we love files. So, let's get into DuckDB. Just in case none of you have heard of what DuckDB is, it is a open source, MIT licensed, in-process SQL OLAP database management system. That's a lot of jargon. Essentially, you can think of it like SQLite for analytics is what a lot of people like to call it. So the idea is that you can basically run these SQL queries directly on files, CSVs, TSVs, JSON, all that good stuff. You don't need to have a whole database running and headaches of client and thinking about all of that stuff is kind of the idea, which is kind of where we get out of the scope of bioinformatics and where we're kind of like, we'd rather have files. It's also really fast. A lot of cutting edge database research is being done on it. L1 cache optimized, if that means anything to you, basically it stays around the CPU is kind of the idea. Go look up some talks on it, it's really interesting. And then also the query execution engine is optimized to do all these things in a very fast way compared to if you tried to use SQLite to do some of these queries. The other thing that they claim, it runs anywhere, as all good tools do. On the cloud, on HPC, on your laptop, on that old Mac in your lab that won't die. So, just to kind of give you an overview of the picture, that came out really faded. Up there on the top left is SQLite, and then you have DuckDB next to it, just to give you an idea of those are both in-process databases versus the client-server model, which would be like Postgres, or now ClickHouse if you're up with the times on like doing analytics on those. So, just a little bit of DuckDB there. It's coming out really tiny. Hope y'all can see in the back. So, you can see that we're actually querying directly from S3 here, and we're querying Parquet files. We'll talk about that in a little bit. You can see some wildcards going on in there, various globbing and whatnot, and so we can just run these queries directly on those files. Can also work with local files as well, which is important. And then you can also query from data frames, and we'll talk about that in a moment. And then you can also just hit random HTTP URLs. Kind of reminds me of something. So you can also use it with a lot of popular tools, such as pandas, just kind of baked in there on this. And the main point down there is you can see the my data frame is where the querying is coming from. I wonder. Yeah. So another thing that might be of interest to some people is it's also PySpark compatible with an API. The main thing that it does is you just swap between, so this line here is just getting the environment variables, and then these are just pulling in the DuckDB version of the function, and then this is the Spark session from that, if that makes sense. So it's just pulling one or the other, and then the results of it is DuckDB spins up a lot faster locally. Obviously, Spark you can scale a lot more, but it's great for these small workflows that people may have just doing quick little queries, and you don't need to run a whole Spark cluster. Okay, and another recent addition is a group has developed a plugin for DuckDB that then allows you to pull in biological data formats. That's really interesting to us here. So, such as GFF here is what this example is showing. So we're just querying a GFF file, and from those, pulling in all the gene annotations, and then this would just print all the gene annotations here on those. So let's talk about Nextflow and DuckDB and some examples on that. We had some recent Slack discussions on we wanted to make an NF core module for it, but we didn't know what the best way to kind of bundle this up. So I kind of went down the rabbit hole, so bear with me here. So what we're looking at here, this was a recent discussion that came up in the Nextflow Slack as well, was using, they were basically talking about building a Parquet plugin for Nextflow to start reading it, and they realized they could just use the SQLDB plugin to read the Parquet file. And so what this does here is we're selecting from the Parquet file, and then if you run that in Nextflow, it will just spit out all of those from the Parquet file, which starts to become really powerful, as then you can start to query all of these outside, and while Nextflow has great built-in functions for those, you can start to utilize SQL queries to ask questions of your data. So another thing that I've always been thinking about as well is looking at data engineering and looking at popular tools like DBT. I love to keep up with software tools for whatever reason. And so on the left here, that would just be a DBT syntax, and you can see the ref, and they're staging customers in. There's a whole lot of stuff going on the back end, to be fair, and then also on Nextflow, there's a whole lot of stuff going on the back end. But basically, we can kind of go one-to-one on those two and use the Nextflow syntax there. So that's just the DBT syntax, and then now the Nextflow syntax that would be the equivalent is down there with the staging customer file in, and you can just have Nextflow stage it for you, which I think is pretty cool and equivalent. It's very, very popular in the SQL space. So let's talk about staging files for a minute. This is kind of an anti-pattern that I don't love, but it's part of it. So we all know you stage a file in Nextflow, pull it in with this. So what we're doing here, pulling in a CSV, and then we're reading from that CSV with DuckDB. You can just use it as a CLI command, just like this on that, so it starts to become really powerful in Nextflow scripts. And then we can also use stuff like greater than, and then we can just say, use this variable and pull it in with DuckDB and start to do some logic based on that. So DuckDB, however, also already has its own plugin that does something very similar to the Nextflow function, which is the HTTPF plugin. And all the way down there at the bottom, if you can see it, we have the link, which is just the S3 link on my iTest here. And then you can see the read CSV down there. And so that's letting DuckDB actually stage the file itself and pull that in. Not the best practice in Nextflow, but it becomes really powerful when you start using formats like Parquet, because you can just pull the columns that you want from the Parquet file rather than staging the entire file with Nextflow. I need to do some comparison of that with Fusion and pulling Parquet natively with DuckDB and see which one's faster as well. Okay, so another little rabbit hole here was I started to think, well, okay, could I use a template file? Because these files start to get really long with the queries. And so you just pass it a bash file, and then you can start to use all this templating and whatnot. These are actually DBT queries that I just kind of swapped in with Nextflow on those, and you can just start to pass all these files in rather than having to have separate tables. You can just write to files like you're kind of expecting to in bioinformatics. And then next, I went down another rabbit hole of like, what if we start to pass the query directly to DuckDB? So you kind of pass it in as a variable to the process, and then from that query, then we can then run it. And you're kind of wondering, okay, why would we want to do that? And so my thought behind this was all of these new AI tools that have come out that write SQL on all this data. You can have a process that's running that, pull that in, and then next you can run your tables on that and start to ask questions of it and generate these things. Okay, so you can also use an SQL file as well as a native built-in DuckDB thing. So there's the file up there, and we're passing this in actually with Nextflow itself in the project directory. I can get to use the bin directory. I don't think DuckDB is smart enough to do that inside of it. And so then we're passing this file query down there, and then we're going to pass next the CSV and just cat it into DuckDB, and then run that query on it. As you can see, then we're passing our CSV, which is the Netflix top 10, and then going from there. So the problem with this that I found was that DuckDB doesn't really like the Nextflow variable replacements sitting in its SQL files. It started to throw errors with that. So I didn't really love that. But I came up with a little idea that I haven't fleshed out entirely. But there's the template function in Nextflow. What if we had, so like first, I really wanted a shebang instead with DuckDB, and then you can just run an SQL file just natively from that. And I think that'd be a really cool feature. But that's more on the DuckDB side, just that. But I wanted to have a like SQL template from that, and then from that, basically we can start to have a little line here, which is just the SQL, and then that will pull in the CSV. And what that turns into is that down there, which is DuckDB-C. And basically just wraps that. So, what's the catch with DuckDB? What do we kind of need from this? Everyone will tell you it's great if it runs on one machine. We have really big machines now. That's fantastic. If only there was a tool for orchestrating single machine processes at scale. So I kind of like to think of it as the internet question of, would you rather fight a horse-sized duck or 100 duck-sized horses? And so what that ends up looking like in Nextflow is then you can start to use split, and like you could split up a giant CSV, a giant file that you had, and then start to run separate DuckDB processes on this so you don't need to rent out a huge machine. Interested to hear if anybody has any actual use cases for that, but just kind of a thought. So found some anti-patterns talking to Abhinav about this. Essentially, if you're running it with the Nextflow SQLDB, that plugin is designed to be a client, such as like Athena, BigQuery, Postgres, and act as that. So the problem is it could put pressure on the head node if you're running your DB on the head node and crash your job. So don't really recommend that, although that is totally possible with it. But there's a new service as well called MotherDuck that will be out that could also alleviate this, and you can just push your queries out to the cloud and creates that client-server model. So some ideas for use cases in NF Core. We have the new NF Core CO2 footprint plugin coming out. We can query that, and I can answer for all my GitHub action sins as well. And then also, we can also start to query on build for what's the most used module in all of the pipelines on that. Okay, so another aside, if I've not thrown enough jargon y'all's way. So there's the medallion architecture, which is another modern data stack thing that Databricks coined. So you have your bronze data, which is your raw data integration, the silver, which is then starting to be filtered, cleaned up, processed a little, and then you have the gold, which starts to be like business aggregated, read counts, et cetera, in the bioinformatics world. And then I was kind of looking at this and learning about it, and I started to look at it, and I was like, well, I mean, multi-QC kind of already gets you to silver, doesn't it? And I was telling this to Graham, and he said, I just thought multi-QC was a pretty HTML report. Edwin Miller. A little office quote there for everyone, or reference. So multi-QC also cleans your data, in case you didn't know. And the multi-QC data and the multi-QC data JSON, it has all of these samples and all kinds of data in there. Everything that you see in the report is also in the data JSON. And coming up soon, it will also be in Parquet by default with the Pydantic rewrite coming up. So we'll be able to query all these things, use Iceberg, all the fast modern data stuff, just kind of out of the box. So we can start querying that then. So I just threw together a little query here from the multi-QC outputs in the AWS megatests for NF Core. This one's just pulling in some SAM stats from that and just from RNA-seq. So just pulling in the samples and the various results of how many reads were mapped and paired, just to kind of get you thinking about that. So let's talk about MegaQC. It's essentially multi-QC for your multi-QC. It's another one of Phil's projects. I love the idea. I really wanted to run it. Oh, that is really faded. Basically, that's the output of all of it, and then you can see the various plots coming up and all of the different samples from that, and it aggregates all of your multi-QC reports into one giant report. It's kind of the idea that then you can query and dashboard on that. However, I wasn't able to get it up and running. I don't know what the state of it is exactly. So we can then start to kind of think in aggregates on these from that, just using DuckDB rather than needing to build out all of multi-QC and start answering these questions right now from our data lakehouses that we've built inadvertently. So we have the read CSV up there going and pulling in the file names on all these. This one's just pulling from Sarek. And then that just pulls in all the samples and pulls in the reads mapped and paired as well. Just to kind of get the idea, the main takeaway here is the wildcard in there that allows you to query all of the results files in the AWS S3 bucket. So with that, we've already built the data lakehouses that we need unknowingly. We've skipped over the whole part where we pay a bunch of money to have our data in databases. And with DuckDB and Nextflow in combination, we can capitalize on them. Thank you.
Great, we've got at least 3 questions here. One was around the writing this as a plugin. Was there any kind of need to write as a plugin? Did you think about that, or was it just standard enough to use it as a command line tool?
Exactly, it's standard enough to use as a command line tool. I did not write a plugin. There was a SQL DB plugin that already had access to DuckDB ahead of time.
And then kind of more related to the application here, could you elaborate on how DuckDB and Nextflow can be integrated to optimize simplified data management and workflow automation? Additionally, how do these tools address the unique challenges of handling genomic data sets?
To answer the first part first. Pulling in all the various samples, you could generate a sample sheet on the fly is one thing that we've talked about. From those, pulling in like, okay, we want the top 10 data sets on this with the highest read quality or whatever, and generating those on the fly, building a dashboard from that, or kicking off Nextflow runs from that. Remind me what the second part was.
Yeah, me too. It was around, like, additionally, how do these tools address those challenges? Yeah.
Right, so, and addressing these tools, it basically allows it to, you could throw this in a Nextflow process, generate it on the fly as your workflow is going, or ahead of time, run this in a separate job without much overhead. Pretty easy to get started is kind of the idea.
Cool. I can give a little bit of color as well on how MegaQC has evolved. So we're also looking to expand multi-QC's use and really kind of aggregate that work as well. So I know that we haven't had a bunch of time to work on MegaQC recently, but it's something that's going to be resurrected in the future as well. Cool. A round of applause for Eben. And next up, we have our speaker, Robert, who's going to be talking to us about Vtopia.
right, hello everyone. I'm Robert Petit. I'm from the Wyoming Public Health Laboratory. It's out west here in the US, one of those rectangle states. But yeah, I'll be talking about some enhancements I made to Vtopia for ongoing genomic surveillance. So let's start off. What is Vtopia? Well, it's an end-to-end Nextflow pipeline for the complete analysis of bacterial genomes. In just a few simple steps, you can go from your raw sequencing data to just a crap ton of results to sift through. Literally sometimes. Sequencing, so let's start at step one. You can sequence your bacterial genomes. It accepts Illumina and nanopore data, or you can use a combination of the two. And then at step two, you got to install Vtopia. It's easily installed through Conda, and your analyses can be done through Conda, Docker, or Singularity. And then step three, there's a prepare command to create a sample sheet if you need to that allows you to process a single or tens of thousands of genomes, whatever you need. And then step four, the previous lab I worked with, we utilize public data a lot. So there's a search command that allows you to query ENA and SRA and automatically find matching accessions and download those and process them in Vtopia. And then, you know, it's built using Nextflow, so all the executors that Nextflow supports, and it supports a lot, Vtopia supports those as well. So with simple parameter changes, you can go from playing on your laptop to your HPC to any of the major cloud platforms. And then step six, we're finally processing your genomes. Vtopia includes more than 150 bioinformatic tools into the pipeline. Its goal is to be end-to-end. There's extensive version control and data provenance, and the idea is after this initial run, you have all your outputs in a nice standardized directory structure that you can then pass to the Vtopia tools. And the Vtopia tools are kind of my favorite part. These are 60 additional workflows that you can make use of the already existing outputs. These allow you to do complex analyses relatively quick and with little effort. That includes things like pangenome analysis in bacteria, which is a bit different than the human pangenome, which we'll learn about here shortly. But you can also do taxonomic classifications, create phylogenies, do all your AMR and all sorts of species-specific analyses directly from those outputs with little effort. And then finally at step 8, you're stuck investigating all the results so you can write that paper up at the end. Or let your epidemiologist know what's going on. But so just to kind of sum it up, Vtopia streamlines the analysis, enabling users to focus on their science and outcomes, which is very important for me because most of the users I work with at Vtopia are not bioinformaticians. They're just people who've been getting data that they need to process. They're already up to their necks and just sinking. And so this idea of making it easy and keep moving is essential for me. But as the bioinformatician, I recognize the need for some revamps in Vtopia. This is the main pipeline in version 2 of Vtopia. It includes all the essential bacterial data analysis steps, your QCN reads, assembling genomes, annotation, sequence typing. But it only supported one species per run. You could run any bacterial species on it, but you couldn't run them together. So you couldn't process your salmonellas with your E. coli. So you had to run them separately, which is inconvenient when you're getting multiple different species coming into your lab to be sequenced for ongoing surveillance. It was also very difficult to merge the results from multiple runs because the idea was you would already have all your data and then you would analyze it and do your work. Ongoing surveillance, you're getting data over time. And we can't wait to notify our epidemiologists that, hey, there's an outbreak going on, but I'm waiting, a year from now to acquire all the data to analyze it. There was also a number of steps that relied on input data sets. There was a script to automate this. But yeah, that's a lot to ask for new users. Hey, you need to build all these data sets before you can run Vtopia with all these additional things. Also, if you're doing multiple species, you need to create a data set for each species that you're working with. I also maintain the Docker containers and Conda environments for each one of these steps, and that can get quite tedious over time. And not all modules were true plug and play. All the Vtopia tools, they're available from NF Core modules, so they follow that NF Core modules practice. These modules did not. These were kind of the core ones that didn't quite get converted when I released version 2. So to give you an idea, a simple genome here, it expected the FASTQ files to come from this QC read step. And you couldn't really move these around. And that is way too strict for me. With all this, it made the version updates just a huge hassle. If I needed to make a quick patch, sometimes it's easier just to ask the user to go, hey, change this line of code, which is not the way to do it. But if it could save me a weekend, please just change this line of code. So I put myself in this situation where this flame was just growing, and it was not fine. So I started working on Vtopia version 3 with some main goals that I wanted to meet Wyoming's public health pathogen surveillance needs, while also lowering the barrier of entry for new users, and reduce the long-term maintenance burden on myself. That's probably the biggest thing I was aiming for here. So by doing this, I streamlined the pipeline. We still include the main steps, QC, assemble, sequence type, annotation. But what's nice now is you can mix and match any number of species per run. You can mix your salmonellas with your E. coli, with your streptococcus, with your staph aureus. There's no need to run separate runs for any of them anymore. It's also easy to use the results from multiple runs. So since we're getting samples over time, I changed it to where now each sample contains all the data it needs. All the results for each sample is self-contained, allowing you to move them around and compare across runs, no problem. The data sets are also baked into the process. Users no longer have to go and build data sets. This is automatically handled now, which is, again, they can just go straight to processing data instead of, oh, by the way, you need to run this first. I also delegated the containers and environments to Bioconda because the infrastructure is there, and why not take advantage of it? And all modules are now plug and play. So all modules now follow the NF Core modules best practices. So all these modules here that you see are treated just like the 60+ Vtopia tools. And overall, this makes the whole version update easy and seamless. If I need to make a patch, I make a patch. There's no sort of, oh, do I need to spend the whole weekend working on this, sorting this stuff out? So in my mind, at least, I had essentially flipped the scenario. I would much prefer to be in a room full of puppies than a burning room. So I truly believe I met that, but I really quick wanted to explore this plug and play bit for Vtopia. So all these modules are plug and play. There's 30+ not listed here. But for each module, I packaged a Nextflow config file and a params.json file. So it'll automatically pull in the corresponding config file and the params.json, which will feed into the CLI, which is taken from the NF Core template there. But in my mind, I can start treating all these as building blocks. For example, and this is a question I've been asked, I don't want to run the whole Vtopia pipeline. Can I just take pieces of it and do stuff with it? So for example, one I got recently was, I just want to call SNPs and indels against this reference for all these samples. I don't want to assemble the genome. I don't want to annotate all that fun stuff. So essentially, you could take the gather module, the QC module, and the SNPy module. And now you can essentially skip all that extra stuff and just go straight to calling reference, calling SNPs and indels. Additionally, if you wanted to look at insertion elements, you could toss in the IS mapper module as well. And so now you can kind of start picturing how we can rebuild stuff and all that fun stuff. To give you an idea, I reshuffled some modules for some new named workflows in Vtopia. The first one is clean your reads. And this idea is I don't want to run all of Vtopia, I just want to QC some reads with the addition of removing host reads from there. So yeah, it's just a simple pipeline, gather your samples, scrub the reads, and then QC them. But the nice thing is you still get access to all those additional Vtopia tools without having run the full pipeline. So if you wanted to, we could replicate that SNPy thing by just running the clean your reads and then the SNPy Vtopia tool afterwards. In addition, I have one called Teton, which is named after the Grand Teton Ranges in Wyoming. But this is another simple one where we want to scrub the reads to make our Office of Privacy and Security happy, so we can confidently say, hey, we did the best we could to remove all human reads from these samples. And then do some basic taxonomic classifications. I underscored basic there because at this point, I just want to know, did I sequence what I thought I sequenced? And also, is there any potential contamination in here? And so we run this on all our newly sequenced samples to where they hit the cloud infrastructure, and then they get scrubbed, and we get a basic QC on taxon information before we run anything. So that would apply to our viral, fungal, and bacterial samples. So there should be some folks in the audience, how's this any different from NF Core tools and using NF Core tools to rebuild stuff with the modules? And so for me at least, this is a way to allow people to reframe Vtopia without having to relearn a new toolkit. In my field, at least in public health, we're usually understaffed. And having to retrain folks can be quite difficult. And by being able to give them a mechanism to reshuffle modules, they can now do all this without having to relearn a new toolkit. Because Clean Your Reads and Teton take the same inputs. If you know how to use Vtopia, you know how to use Clean Your Reads and Teton. And that's the idea behind here, where we can reduce that training time. So yeah, let's go ahead and wrap this up. Vtopia version 3 has been rebuilt for ongoing genomic surveillance of public health pathogens while improving the user experience and significantly reducing long-term maintenance. I think users tend to be happier with this new version. It seems easier to use. But me personally, I no longer feel like I'm in that burn-in room. I feel like there has been a significant maintenance burden reduced in Vtopia, which is quite nice. Briefly, a lot of people to thank, many of the folks in this room. All the developers of open source software, there's so many. On the doc site, you can go and get links to all of them. And the many users who are regularly providing feedback and suggestions. The Bioconda folks, Nextflow, NF Core, Sakara. My colleagues from Wyoming Public Health Laboratory, Taylor, Chase, Jim, Rob, and Joe. Taylor and Chase give me great usability feedback, which is super awesome to get. Tim Reed and the Emergent Group over at Emory University, and all these GitHub users who provided feedback while I was developing version 3 on, what could we change, what could we improve. And then finally, the Georgia Emergent Infections Program and the Centers for Applied Pathogen Epidemiology. Thank you. With that, I'll take any questions.
Great, thanks a lot, Robert. It's been fantastic to see public health in terms of their adoption of Nextflow, and it's really driving things forward. We see a lot of it in the CDC with some of the public health labs as well. I think the work that you're doing is really making a big impact there, and it's really changing folks as well. Got a couple of questions here. It's really good to see the convergence with NF Core related to the modules. Can you provide us with a kind of a quick summary of what are the key differences though between Vtopia v3 versus like a standard NF Core pipeline, and maybe some of the design decisions that you made for that?
Yeah, so I think I have a bit more flexibility because I'm not trying to fit a bunch of different pipelines into a single framework. I do add some stuff to the modules. That doesn't mean it's better or worse. It's just different, including additional login information and some additional version information. But I think it's one of those where if I were building this pipeline in 2023, I wouldn't have done it this way. I would have gone to NF Core tools and downloaded all the modules I'd need and glued them together. Unfortunately, this goes back a long time, and so I didn't have that option.
Okay, that's good to hear. And what do you see as the main challenges today, even with version 3 that you've developed, for biologists to use Vtopia or kind of similar pipelines in a more autonomous way?
Maybe this kind of initial fear of the command line. So each of the people I work with in Wyoming they all are quite comfortable with the command line. And I think once you get over this initial fear of the command line, this black box, you open your world to a whole slew of different things. And there's obviously those, hey, I'm trying to work on this HPC system, but that's universal to everybody because each HPC system has their own restrictions, that's just kind of, we just take it a comment at a time on the GitHub issues.
Cool. And final one, related. How do you see like what the work that pipeline developers can do to make those pipelines more accessible? And what's the kind of steps that you take in the development of Vtopia for making it more accessible?
Make it easy to use. The attention span is going to be short. If I have to go and build a bunch of things, it's difficult to install. That's going to put a huge hurdle on actually wanting to use it. For me at least, yeah, making it easy to install. Taking the NF Core module approach, because a requirement for NF Core modules is it has to be on Bioconda, or it has to be available from CondaForge. You've already solved the installation issue. And then that you have the containers and all that. But yeah, make it something that you yourself are going to use as well, so that way you find the bugs. And yeah, something that you feel like you can hand to other people and allow them to break it. I enjoy stuff getting broken. So that way we can fix it and figure out why.
Awesome. Well, good luck with the rest of your weekends then. Yeah. Awesome. Thanks a lot, Robert.
Thank you.
Next up, we have Maxime, who's going to talk to us about Sarek.
Hello, everyone. Yes. So today I'm going to talk about like Sarek. I think it's been like a while like since I presented like Sarek like in a Nextflow event. So I'm quite happy because like I usually like let that honor to other members of the community, because for me Sarek has been like a project I've been working on like for a while, but it's also been like a community project, and I think that's important. So quickly, what I'm going to talk about like in this talk. So I'm going to talk about like the beginning of the project. What are the core values of this project? What is actually Sarek? What is the current status of Sarek? Which might be like a bit of a redo of what Ricky presented like in Barcelona. What are the plans like for the future? And am I really trying like to conquer the world with Sarek? So the beginning, how everything like for me, like one of my core values is like reproducibility. If what we are doing like is not reproducible, then we are not doing science. Like we are not even like cooking, because whenever we are baking or whenever we are cooking, we follow recipe, we try to follow like exact stuff, and we try to be reproducible. So if we are not even doing that, then what are we really doing? So for me, reproducibility is central, and I'm lazy, and I'm like quite paranoid, which is why I use Nextflow, because it's been like such a great help for everything, and I like that. So in 2016, like I just like joined like Barntumorbanken, which is like the Swedish childhood tumor biobank, and basically they had like samples because they are a biobank, and if you have sample like in a biobank, you need like to share them, because otherwise you're just collecting stuff, and yes, it's if you don't share back the data to like the researcher, it's completely useless. You're just like collecting that, and it's not used. So we had samples, we wanted like to share data, and we needed like someone to help us do that. So there was like NGI, National Genomics Infrastructure, which was like the sequencing facility. That's where Phil was working. And there was like NBIS also, bioinformatics platform that had interest into like working together. And basically we decided like to all work together. So yes, I said we, but I'm no longer working there, but yes, you understand. And we all decided like to work together into developing like a single pipeline together. So for me, Sarek, at the very beginning, started as a community pipeline. We were like, I think, less than 10 developers from like 3 different like group. From like 2 different like organizations, and that really wanted like to work together. So we had like to accommodate like all of that, and I think that's why like within Sarek we have like a couple of like core value that are still like part of Sarek DNA, and some of that I guess like got like implemented later on like into other work. But I'm going to talk about that later. So the core value like of Sarek is first community. Sarek has been like a community project for the very beginning. We have like tons of like contributors to Sarek, and I'm only here today to talk about it because I'm the only one left from the beginning. Like no one else has worked like that long on Sarek, and like I'm here today because yes, I'm the only one left. That's all. So Sarek also has been like an open source project from the very beginning. That was like the goal of it, and yes, that will always be the case. And of course, Sarek had been built like using Nextflow, and that's what we wanted, and it's been working like super well. Fairly soon after that, I guess we decided on adding like a couple of like extra value to Sarek. So first, we wanted like Sarek to follow best practice and also to establish best practice. So to make sure that everyone was like kind of following like the same ideas into like how we assume like the analysis was supposed to be run, and how to store the data, in which way to store everything, and like so we wanted like to lead by example and follow like what's the best example we are doing. Exploring in Sarek, we wanted like to explore a lot of stuff, so we explore a lot of different tools. We do a lot of benchmarking. We look at different stuff, and we were doing that like from the very beginning. And because of all that, we do a lot of refactoring. I personally like pulled Sarek like apart and together, and apart again, and together again. And I'm pretty sure I want to put it apart again. Like it's been like back and forth, but because yes, we want to show the best practice and like what will be like the best way like to run a pipeline, and like working within NF Core, I have like some ideas that I want to implement not only in Sarek but within like the rest of the NF Core community. And for me, that's the best part of like being able to work like in a community like that. So what actually is Sarek? So Sarek is like an analysis pipeline to do some variant calling. So we start with like some sample. Usually we start, so what we were doing like at the biobank, we had like some blood sample, which was like the normal sample that is used to do some normal analysis. We had some tumor sample that is done like to do some tumor-only analysis. And then with both of them, you can do some like paired variant calling, and you get like, you know, the mutations that are in your cancer cell. And that's the whole plan about Sarek. So we had like initial clear goals for Sarek that we said, okay, we need to set up some limit, and we are never going like to go across that. And like, yes, pretty quickly, all of these limits were like completely irrelevant. The first thing we said that, okay, we are going to use Sarek only for like research purpose. It's never going to be used like in a clinical setting. That, yes, no, that was quickly like forgotten. We said at the very beginning that we are going to use Sarek for only tumor normal analysis. It was only to be used like in a cancer setting. And at the beginning, Sarek was called the cancer analysis workflow. And we did a rebranding as well. So we rebranded like as Sarek. And basically, we rebranded that because we figured out that it was a complete mistake. We realized that when we forgot to specify the tumor sample, like within the sample sheet in Sarek, it ran like the complete like germline analysis without any issue. And by doing that, it was by mistake we replaced the old like germline pipelines that they used to have like at NGI that was like out of date because it was only supporting GRCH37 data, and we created like a new pipeline like for NGI completely by mistake. And that was actually like fun, so that was nice. Then we decided that, okay, Sarek should only work on like whole genome sequencing. Yes, we got rid of that as well. And only human data, and yes, we got rid of that. So for whole genome sequencing, like Sarek, basically when you do variant calling and like pre-processing, it's super simple to make it work either on like the whole genome or some smaller regions, so either the exome or like targeted sequencing on like panels. And that worked like flawlessly because it's just tiny amount of like params that you need to change or like whatever. So that was simple to implement, and it has been like part of Sarek like for the very beginning. Yes, at the beginning we also said that we wanted Sarek to work only on human, and then we got like a first collaborator that came and said, "Oh, I want to work on mouse. Can I use Sarek for that?" And I was like, "Okay, yes, we might need like to tinker a bit with the dbSNP file and like see what we can do with that." And then yes, it was working. So we rendered some of these files like as parameters. Some of them were like optional, and then someone else came like with I want to analyze like dog data and so on. And so we render like a lot of the step like optional. We added like some extra variant colors, and that's how Sarek like became to be like this beast of a stuff, because like every time someone wanted like to add something, we added stuff like to Sarek. And then at some point, that was also something that we decided that we didn't want to do. We decided to add Sarek to NF Core. And I think that's like the main point of like why Sarek is such an oddball within NF Core, because Sarek has been started like as a different like project than NF Core. And for me, a lot of the logic that we have within Sarek has been like some of the building blocks that we use for NF Core as well. We have like for some historical reason, I don't remember everything, but some of the logic we use, like to, especially for the test data set, some of the config files that we use was like from Sarek as well. And then, like, of course, a lot of the stuff were like from our own like pipeline, like within NGI. But then, yes, Sarek was important there. And Sarek is completely like out of scale from all of the NF Core pipeline. We have like this rule in NF Core, which is like, yes, pipeline should be lagom. So it's Swedish, it's like not too much, not too little. And Sarek is definitely like way too much. But yes, it works well, and that's what make it work. So yes, that's why like Sarek is like this weird within NF Core, because it has started like as something different and then ported into NF Core. I think an interesting question. So why Sarek? So on Slack, Florian was like super interested into knowing why Sarek was named Sarek. So he asked like ChatGPT, and according to ChatGPT, Sarek is really like a Vulcan character. It's the father of Spock, but from Star Trek, obviously. But that's not why we named Sarek Sarek. And according to ChatGPT, like we use Sarek because it was a nod to the logic, the precision, and the advanced technology associated with the Vulcan race in Star Trek. And I do like this definition because it's like super smart, and I love that. I would love to have like come up with that, but no, that's completely not true. Sarek is actually like a national park, like in northern Sweden. It's pretty inaccessible. There are actually like no roads that lead like to Sarek, so you really need like to walk in and explore. And the landscape around Sarek are like completely beautiful. And like so the name actually is an allegory like for the genomic landscape that we want to explore with the pipeline. So that's how we came up like with the name. And that's actually how we came up also with the logo. So that's why the Sarek logo like is a mountain. This is a mount like Skirfre in Sarek. And we had like a very lengthy exchange of email with Phil Marcel, Björn, and like other developer at NGI. I think it's like more than 50 email. And one of the last comment like from Marcel was like, any chance you can make like the mountain top like less pointy because it hurts my eyes like so bad. So yes, that's why like the top is slightly less. It's slightly like cut off. So that was a very like fun exchange. And actually, with each Sarek release, we're exploring the national park. So every code name for a release is either a summit, a glacier, a river, or like a random point of interest within the park. Some of the names are like completely weird because they are in the Sami language from like northern Scandinavia. Some of the names look like very similar from one to another because sometimes they have like the old like Swedish way to spell it and like the new Swedish way to spell it. So it's a bit of a mess, but yes, that's classical. And Florian again had like very like a lot of fun with within the AI cafe, and he came up like with a nice mascot like I guess it's like the NF Core detective that goes around like Sarek to detect the variant. And that was like super fun. I find this one like so cute, so I wanted like to share all of that with you. So the current status of Sarek. So Sarek, as I said, like is a whole genome sequencing like analysis pipeline, so exome and like targeted. So we can start like from multiple point of interest within Sarek. And like as you can see, like for me, Sarek is like really like 4 different like block. And like we have one block which is like the pre-processing, which like follow all of the GATK best practices. One block which is the variant calling, and in the variant calling we do like either like in the blue line, that's just the normal variant calling. In the red line, like at the bottom, that's the tumor-only variant calling. And in the middle, the red and blue line, that's the tumor normal variant calling, like all together. And we do like, we get information about like SNP and indels like from deep variant, free base, haplotype color, Centiyon haplotyper, MPileup, Mutec2, and Strelka2. For copy number variation and structural variant, we use Manta, TDIT, ASCAT, and Control Freak, and CNV-Kit. And we have like MSC Sensor Pro for the microsatellite instability. And then for the annotation, we use SNPF, Ensemble VIP, and we actually just added like a BCF tool annotate at the last hackathon. So we had like a couple of like new features in like this year. So I'm like, this is the slide that I copied like from Rike that I updated just a tiny bit with like with Simon like adding like NGS checkmate. Becky had worked like into adding like joint variant calling with Mutec2. Anders has been working on like adding like support for Centiyon. I've been working on my own stuff with like adding like annotation cache and trying to do a tiny bit of refactoring so we can only like we can just build only the indices that are needed for Sarek. And then Edmond and Lasse has been like I've been involved a lot with like benchmarking, and Rike obviously has been involved like into everything. For me, like being able to work like with a community with such like nice colleagues, we have like a Slack like group dedicated for the developers that are a bit more active than just the regular user, and we try to exchange ideas about what we can do to improve Sarek, what we can work on, and then we help each other into like working out on Slack on the different issues that user can have. So a couple of like ideas for the future, and like I've seen like a lot of you doing the hackathon, so I think like nowadays you're all like contributors. So if you want to come and help us like avoid stuff like within Sarek or within NF Core, you're welcome to join, and that will be super interesting. So a couple of stuff that we are going to add. So Anders is going like to continue working on adding like some Centurion related stuff. Pierre is going to add like some coverage like tool. Rike is working on adding Velociraptor and like trying to be smarter, like even smarter with the benchmarking. Francesco has been like very involved with like Parabricks implementation within Sarek. Raquel has been like looking into adding like some math support within Sarek, so that could help us like to go forward with like the annotation and be smarter about what we do. Adam, Abhinav, and Venkat have been working like during the hackathon on like Azure Megatest. So I'm hoping that we will be able to have like that soon within like the pipeline, and pretty sure also as well within NF Core. And Adam, Satish, and I have been working on like refactoring the pipeline, like following what we were doing like with Arshil and Adam and like everyone like in the NF test and the RNA-seq pipeline, and then trying to integrate all of the NF test. So do I have actually like any plan for domination? No. My whole plan, like actually within Sarek, is like to really follow like the evolution of Nextflow and to keep up to date with like whatever we develop within Nextflow. And for me, being able like to like working at Sekera bring me like closer to the Nextflow developer, and that's actually super nice. And I just want to thank like everyone that either like was involved within the project from the very beginning, or either did a pull request on Sarek. And Paolo has made a pull request on Sarek? You did? And I, like tons of people have worked on Sarek, and I'm very like proud of that, like to have been able like to do that. And like I'm super happy with like all of the collaborators that are like become like good friends as well. And I think the stuff that I'm the most proud like within Sarek is that the developer of Sarek doesn't need me anymore. They can like do like release without me. They can like continue updating and maintaining the pipeline without me. So for me, it's more like just a joy like to continue working on Sarek. It's not a burden at all, and that's fun. So thank you very much. And if you have any question, now is the time.
Okay. We've got quite a few questions for Maxime. The first one is can you expand a little bit on the clinical use cases of Sarek? I think it's asking more around if you have specific examples of which countries it's been used, obviously without disclosing any sensitive information.
Yes, so like I know that at the biobank we were like looking into like using Sarek in like some for some like clinical cases. It was like a collaboration within like some other team like within Sweden. I've been in contact with some hospital like that are using Sarek and like are making some like their own like either they have like their own flavor of Sarek and they add like a couple of extra stuff, or they just like using Sarek as is. So for me that would be like the case.
Yeah, it'd be great if folks are using it as well in other examples. It's always great to get that information.
Yes.
What do you think, is there any plans to include any work on it with acceleration, so with regards to like Dragon or use of GPUs?
So yes, we are like, as I was saying, like we are planning to add like Parabricks. We already have a drag map, so the Dragon like aligner from Illumina, and yes, we have like Centurion. So yes, we love to add like more stuff to Sarek. Like for me, like yes, the more stuff I can add to Sarek, the happier I am.
And then any kind of comments around what you're doing for testing? Like when you're doing a release of Sarek, I know there's a lot of testing which goes on. Obviously related a little bit to the NF Core test suite that goes on. Maybe you want to comment a little bit on that?
Yes, so I'm pretty like paranoid about tests. And so basically, currently in Sarek, what we're doing, we like completely split up the whole logic of like the sub-workflow. Each sub-workflow has its dedicated like config file. And whenever we touch like the sub-workflow, like any module that belong to a sub-workflow, any script that belong to the sub-workflow, or any config that belong to a sub-workflow, we do the test only for this part, the test that correspond to only this particular sub-workflow. So we already have the logic that we want to reorganize, like with NFTs that we devised, like with Archive, and we just want to implement like all that within Sarek. And then before we do any release, what we do is that we ask like other developers that have access to an HPC if they can run like the sample by themselves and like to see if it works as well. What we are planning like in the future is to like, and that's what like Ricky has been working a lot, is to have like some genome in a bottle data and to look at the actual like variants that are produced and to see if we like keep on track with like the precision, the recall, and like all of that. So for me, the next step will be like not to do the accreditation because I cannot do that like in an open source setting, but to actually help any user or any customer to do that themselves. If we can like just push them into doing that, that will be amazing.
Yeah, that validation and making it easier for users is kind of key. There's a few more questions in there, but I'll leave it to you to go and to answer in Slack. Awesome. Thanks a lot, Maxime.
Thank you very much.
So next up we have Rosie from Element Bio, going to be talking to us about getting started with Element Bio and Sakura.
Okay, great. Hi, I'm Rosie, and I'm from Element Biosciences, and we've been working with Sakura and have some very exciting things to share. So just to set the stage, kind of the question or the story that a lot of people have is we have some sort of sample, we're going to sequence that sample, and now we need to do analysis on it, and why do we need to do that? We need an answer for whatever question it is. So this is obviously clinical, could be plant, could be agriculture, whatever, very, very generic problem there. But sample to answer is what people always really want. You don't really care about sequencing, you care about your question that you're trying to answer. So our sequencing machines, they put out base call files, binary files. And no one really knows how to read these if you're not really experienced in that area. So that needs to be turned into something that is readable. In order to do that, you have to take your data off the sequencer, you have to put it somewhere, you have to know where it is, you have to be able to view that, explore it, give it to people, spread it around. And then you actually have to do that conversion into that readable format. And that's a FASTQ file, which is kind of the most common file that people are using right now. And that goes into a lot of secondary analysis. So if you get a FASTQ file, your world is opened up, especially to a lot of pipelines as well. So how do we get this story from sample to answer out there? Well, there's a lot of problems and questions along the way. So how do I get affordable but high quality data? That's number one, you need to get your data sequenced. Once you have it, where do I put this data? Cloud, local, do I need to buy something? Do I need to pay cloud costs? I'm not sure. How do I run a pipeline? And how do I do it automatically? Because it's usually not scalable to have one person just sitting down and doing everything, especially once you get a whole bunch of samples or you're growing your program. Well, same question with secondary analysis. I've got my FASTQ files, but now I want to get to those great answers. I have clinical insights or something else. How do I do it? Where do I do it? Which pipeline do I choose? Do I build my own? Is there a great open source one that I can already use? And then, keeping going with that theme, how do I make this as automatic and scalable as possible? And the cloud is a really great solution for this, but that is also scary to some people who haven't necessarily had a lot of experience in it yet. How do I learn these things? How do I get involved in it? What do I not know that I need to know? And then after all of that, you kind of have to ask, if you're a small team, do I have somebody who knows this already, or do I have to make them learn how to do this? Or maybe I can't have somebody do it yet, so how can I get that set up? And those all lead to bigger questions in the long run, like once you have this set up, how do I do QC? How do I start to route all this data together in different ways? How do I make it scalable and reproducible? Both really important, especially when you're talking about moving into something like a clinical application. Kind of overwhelming for some people, but we've got some answers to this. So first of all, let's start with sequencing. We have the Aviti machine at Element Biosciences, and this is where sequencing can start with high quality data at an affordable price. So the data has very good accuracy, over 90% Q scores, over Q30, well into the Q40 and above range sometimes too. The instrument has two sides, so you can run dual flow cells, one on each side, also flexible start, so you can start something on Monday, wait, do something on Tuesday, do them at the same time too, with 1 billion reads per flow cell. So you can get a lot of data out of it, but also it's tunable. So we have several different kits. If you don't need 1 billion reads, you can go a little bit lower, go a little bit faster. If you don't need 150 cycles, we've got 2x75 and 2x300 kits as well, so you can really bring your application to it. We have our library preps as well, Elevate, but also Adept, which is compatible with over 65 different existing assays. So if you're using it, you can probably integrate it into your current flow. And the nice bit here is that at the end of the day, you have a really affordable cost per gigabyte or cost per read. Okay, so let's just talk a little bit of data behind that. So VD produces high quality data. Most of the Q scores are over Q40. So if you look at this chart, you can see that that green is well weighted in the 40 to 45 area. And if we look at those Q scores, these are against truth data sets, so we know it and can say, here's what we predicted versus here's what is known. It's very well calibrated, and they fall right on that line that you see indicating that there. This is all explained in this paper, so the QR code is there. The link is at the end of this presentation as well. Go check it out. The data is in there, and there's also some data on long inserts, and it's all on truth data sets so that we can know what it is. So I would encourage you to go check that out. Here's just one other example with some of the long insert work that was done there. So this is PCR-free whole genome sequencing at 2x150, 35x, and HG1 to 4 querial samples, the NIST truth data set for benchmarking. So what we're seeing here is that there is a low number of errors. As you get those long inserts, 500 to 1,000 base pairs, you can see a trend downward each way, so you're able to rescue a little bit of data and get better coverage. So the FastQ data for all 8 of these runs is also public in that data set. You can check it out and try and reproduce it yourself. All right, so you've got high quality data. What happens for your next step? So this is where LM BioCloud with Element comes into the picture, where we start to make these connections for people. First thing is that you get remote run monitoring. So if you look on the left here, that's going to play and give us a little view of what this platform looks like for people. So while it's sequencing, you can get a view of what's going on. You can even plan a run ahead of time, work with some LIMS systems. Cloud storage, bring your own if you want. You can use an Element hosted bucket if you want. That data is going to stream up into the cloud. You'll get a nice view of the data in our interface. And of course, your primary analysis metrics to view and say, how good is the sequencing run? And it's going to explore in-depth Q scores, error rate, indexing if you have it, and give you a venue to do that. Now, the most important part here is that next step. How do we then connect that to an analysis partner ecosystem and make it simple and easy for people as well? So I'll just skip forward to this for a little bit. You can see kind of the end of a run story here is when I get to those data files. I've got these raw sequencing files. What happens next? So we already solved this problem before, and this is a solution that was presented a couple years ago to say, here's how to automate your data. So coming off of a VD, there's a final file that gets written, a run uploaded.json file. You can write an object listener on Amazon if you're using Amazon for that. Say, hey, I found that file. Now go and do something in a Lambda to kick it off with the right authentication and code that can reach out to Nextflow Tower and get your data for you. That is a good solution. That definitely still works. If you have questions about the details of it, talk to Edmund. He knows all about it. It's really flexible, so you can put this on any system. Or if you have an existing pipeline, it works really well. You might need to integrate something in. So this works and is still very viable. But there's some cons. It's a little bit of a manual setup, so it's not necessarily templated out. You have to go and learn how to do that. And again, if you're maybe a person that doesn't yet know this, you need to learn about AWS infrastructure. And that's not always the easiest for everybody, especially if it's, say, your first time getting into that. And then also, it's a repeated infrastructure setup. So let's say you have like 4 or 5 customers and they all do it and you find a problem. You now have to tell all of them to solve the same problem several times. which can sometimes be a little bit frustrating for everyone involved. So we had some ideas about how to make that process a little bit better for everyone. And that is working with LM Bio Cloud and integrating it with a platform like Sakera to centralize some of those steps to be a little bit reproducible. So same situation, the Aviti instrument can always stream to your cloud of choice, AWS, Google, Element, whatever you need. But at the end of the run, there's going to be a run completed event that comes to the event queue, and that's going to set up a workflow trigger. So you do have to configure your workflow, which I'll show you next, but once that workflow triggers with an authenticated protocol, it can reach out to your Sakera platform and launch that workflow. So in the case of what we've done, we prototyped with a basis to FastQ Nextflow that is not yet public, but I hope it will be one day. It's really simple. It's just a wrapper on our basis to FastQ. This is already in Nextflow core, so you can also use it there, but this was just one that we could prototype with a little bit faster without having to worry about impacting anything. Once that is done, you get your nice data files, and again, that can stream to your cloud of choice. AWS, Google, Element. If you're a person that's providing data to somebody else, you can even send it directly to them. You don't necessarily have to build a protocol to like redistribute this data in some way. So what does that actually look like? So on the left here, you'll see LM Bio Cloud. We're big on explaining things to people, because again, maybe everybody doesn't know anything, but you get a simple form where you can connect to your Sakera platform through an authenticated token. And that's going to need to have the permissions to let you launch, so that does have to be set up. But once it is, you can say, great, we're connected to that platform, and then you can set up your flow configuration to basis to FastQ. So you can see that on the right here, and it's a pretty simple model. You have some input locations that are those cloud storages. You have some output locations that are cloud storages. And then you can set up a trigger to either be manual or automatic. So automatic is obviously what most people want, but sometimes you need to turn it manual, especially if you're prototyping or changing something. And then in terms of the platform, that actually looks like this in LM Bio Cloud. So we do a light reporting to say, here's what was executed automatically. You can always see that, but really that data belongs in Sakera platform. So you can monitor the workflow just to, if you were looking at your run, you're looking at your primary analysis, and then it kicks off. You can say, here's how it's going, but the deep stats and everything that are in Sakera that are awesome are still in there, and you can connect to that. You can also relaunch your workflow. You can do it in either platform too. If you do it from the LM Bio Cloud, you'll keep all of your connections to all of that original run data, just so that if you are comparing like primary analysis to after, or maybe in between different runs, it's going to be able to collect that for you. But full data visibility here. So it's really, leveraging each platform's benefit, but not trying to redo anything. So here's just a little bit more information about how that looks. So on the left here, once you get your completed run dial, you have this directory of base calls that you get there. Then we have this kind of platform automation magic that we've described here. You can go check your completed run in Sakera. That's awesome, but the real magic here is on the right, where you just sit and let this happen. It's set and forget once it's configured, so you don't have to be manually doing anything in order to have this set up. So just some summary points here. LM Bio Cloud, what it's really helping you do is leverage automation so that you can get to that hands-free goal for that first step of FastQ analysis via event-based actions. So not relying on the file, but relying on events that you can replay, retry, and also expand into different actions in the future. Really importantly as well, this goes to your cloud storage of choice. So very flexible ecosystem to use wherever you need your data to go. It's your platform as well in Sakera. You're just connecting them together. The really nice thing I love about Sakera is it's great, it's easy. If you aren't an AWS aficionado, there's great things like Tower Forge that will set it up for you. They work really well, really easily. So effectively, with a few clicks, you can get this system set up rather than potentially a few weeks of learning if this is new to you. And then setting up your flow, you have that connected automation from that run complete event, that you can, reuse as many times as you want to continue and relaunch that data. Obviously, you want it perfect the first time, but we all mess up our indexes sometimes, right? So what's next in this? Secondary analysis. Just like we described for this, that's a whole nother problem. Is it a run model? Is it a sample model? Is it both? Is there metadata you need to start tracking? Is metadata uniform across everyone? Answer, never. Everybody has custom metadata. So how do you deal with those questions? We've solved this internally. We have an internal database, and we've done very well with setting it up with Sakara for our pipelines into different things. And we'd like to look at that and say, how do we generalize that? Especially because there are resources like NF Core. So really valuable resources that if you can plug them in easily, we'd love to enable that automation and just letting people string it together without having to do as much work. And the very exciting thing is early access of this is opening February 2024. So if you're interested in a VD or something like this, or this is a problem you're struggling with, please talk to me, and I can get you some resources to get into that. So here's an example of how we at Element have done it. So here you can see that this is our pipeline where we have a whole bunch of different outputs. We've got our alignments, we've got CMPs, we've got everything. And the way to do that is we're aggregating some of our samples, doing our internal magic that we're hoping to generalize. We launch our whole genome Nextflow workflow on Sakara. And then again, we just sit and wait. So this is really nice because someone says, I need a run, and I say, okay, great, I'll call you back in a day when all the sequencing done and our analysis pipeline is completed. So looking to figure out how to share that experience with other people as well. And lastly, just acknowledgements. I'm here presenting this data, but there's a large team behind it who makes a lot of different stuff happen. So thanks really to them because they've done the bulk of this work. Yeah, that's it. So if you have any questions, we can talk about those now. And again, if you have any interest, please let me know.
Thanks so much, Rosie. I'm really excited to see where you go with the next steps of this, particularly related to the metadata. Also something we're thinking about a lot with regards to having registry, linking that data back to the analysis itself, as well as the downstream steps in that. We've got a couple of questions. One is around, have you thought about integrating something like BBMap Clumpify, which is really around compression of those FASTQ files, or are you when you're basically transferring them up into cloud? Are they in some
It's usually pretty fast, so I would say that's not an issue that we observe often. The whole workflow, it's about 30 cents and 30 minutes on the image size that we have. If you don't want to spend 30 cents, you can spend $1 and it'll be an hour. Okay. So it's really like, it's cost of return.
Yeah, amazing. Edmund's been typing a question for a while. No? Okay. Okay, awesome. Well, thanks a lot, Rosie. And we're going to have a break now. There should be coffee and the like around. So thanks a lot.
Thank you.
Oh baby, I wanted you to be here inside my arms where the night goes down. Oh baby, I wanted you to be here when the sun comes up and the day goes by. Oh baby, I wanted you to be here inside my arms where the night goes down. Oh baby, I wanted you to be here when the sun comes up and the day goes by.
All right, everyone. Hello. All right, everyone. We're going to get back to the last session for today, the second session for today. Are everybody having coffee? I hope you're nicely caffeinated, hydrated, energized for the second session. If you can come back to your seats, and we will begin shortly. All right, everybody, thank you so much. Now it is my pleasure for this second session of the summit to introduce Adam Philippi, who is, oh, sorry. I was so focused. Hello again, welcome back. I'm a time traveler. I come from the future, but now I am also very delighted to introduce Venkat Maladi from Microsoft, who is our gold sponsor for this event. So thank you very much for that. Was also a sponsor of the hackathon, which we very much appreciate from the point of view of the community. So thank you so much.
It's great to be back in part of the Nextflow community. It's been 5 years since I've actually given a talk in person. Last year, somehow I did a virtual talk in Barcelona. They worked out okay, thanks to thanks to the team. The time difference really screwed me up, so this is much better. Today I'll talk a little bit about harnessing genomics in Microsoft Azure. And really, what we've seen, the system is really ripe for innovation. And as we've seen in the last year, artificial intelligence represents a lot of what we've been doing and pushing, but it's not the only thing we're pushing. And there's a lot of innovation that can happen in life sciences and what we're doing here with workflows and pharmaceutical companies. So I'm part of a health life science research group, So our mission is to empower every person to kind of live a healthier life, and we're trying to here to empower research, right? And so what we really want to do is kind of have research discovery, do the testing, monitor, diagnose, treat, come back to discovering, developing new tests, and keep going back and forth, right? And this feeds into not only the development of new diagnoses and treatments, but also on how we do development. One of the biggest things we've been doing in the last couple of years is how do we improve development and testing of genomics workflows and kind of democratize the use of the tools that have been developed by the community. Last year, we really worked closely with the community and GitHub and Nextflow. We needed to quickly develop, test, and commit changes in a virtual environment. And so we have GitHub code spaces that we developed that gives us a purely isolated development environment in the cloud. It's customizable for every project. Can run on a different set of VMs, 2 to 32 cores. And it's all in browser, but it can also be run on your VS Code desktop. And what we've done here is actually installed Nextflow, NF Core tools, VS Code linting, as well as Docker. And this provides you with effectively an isolated environment to do all your testing of stubs, development, and pair programming. I used this extensively in the mentor-mentee program last year. My mentee was actually in Australia, and I was in the US, and at midnight we would do pair programming using VS Code, and we were able to quickly test. And we actually used the code spaces as our head node, right? So he was able to launch it from there, and we were both able to actually see all the error messages and quickly debug, which is a great way for us to program. This is one way of helping with the testing and development, but one of the things we've been developing over the last couple of weeks and months is the era of copilots, right? This is AI pair programming, right? So the next evolution of the in-person pair programming. And right now, GitHub Copilot is trained on all the languages that appear in the public repositories. This has some drawbacks, right? It's dependent upon what's available in GitHub and public and the good source of truth for those. Some languages are better than others based on how representative they are in GitHub. And we're seeing a lot more papers and white papers coming out on personalization, customization of these tools. And we are also adding this to GitHub Copilot Enterprise in the next year. But does this mean we actually have a Nextflow Copilot? Kind of. As you can see, if you ask Copilot, you could say, I want a Minimap 2 alignment. It kind of gives you a stub of a Nextflow process. It's not great. It's not perfect. It's a hybrid between DSL1 and DSL2. It doesn't give you Docker images. It doesn't tell you all the options that you want. But if you didn't know where to start, it's as good as a template. But is the response actually useful? Maybe not. So if we actually get this again, we generated Azure OpenAI, and then we trained it on the NF Core modules as examples, which we think is a real good truth data set of how to write good Nextflow pipelines and modules. And what we're able to do is vastly improve what this got us. We're able to get a full process with all the information from NF Core. If the process already existed, it didn't recreate it. It just pointed you to which module to actually just add to your pipeline. What this also did is if you try to tag together a couple different processes, we actually, it's hard to see, but we reference exactly which metadata that YAML, the .nf files that were used as references to build this, right? So then you can always go back and see what is going on and maybe add those. Right, so there's a bunch of differences. Our syntax is a lot better aligned with NF Core. We have the more of the options in a NF Core and Nextflow DSL2 structure. And overall, I would say it's maybe 90% better than what we had previously. But this is where we need the Nextflow community's thoughts. What is important for when we look at Nextflow code, right? Are we looking at syntax? Are we looking at script selection, sections, container sections, tool documentation? Are we getting a summary of what's in the process? Do we need tests and generating those unit tests? That's the next level, right? That's where going to the community and coming back and iterating of what this next model would look like. So our plans are to go with the community, elicit responses on Slack and see if we can test how useful it is. And where do you draw the line, right? Where does it become useful and where does it become a hindrance on actually developing pipelines? What we're trying to do right now is to identify how do we measure that quality. The next thing we're also looking at is how do we get better at understanding the bioinformatics tasks and tools and options that are available there. Right now, not all the tasks have all the tool options in it, and that's part of the gap in training. Can we train it on all the bioinformatics tools available? So I'll be around today and tomorrow, so if you're passionate about Copilot and testing LLMs, please just grab me and we'll talk and we can set up a Slack channel on Nextflow and keep going from there. Additionally, we've been helping with the NF Core community support, providing additional credits so we can test all the NF Core pipelines on Azure. We've been working on the Azure mega test with Sarek, so hopefully once Sarek passes, I think all the rest of the 99 repositories should easily pass. So fingers crossed, we'll get there. But one of the biggest other hurdles that we've been seeing is how do you deploy your pipelines in the cloud? Nextflow makes it pretty easy with configs, but there's a lot of data tools, community-driven activism, stakeholder sponsorship. There's a lot of problems with this. So we don't want to proliferate another standard, but we are proliferating another standard. But we're working with the community, with the GA4GH community, to develop the task execution service API. The idea here is that it's a lightweight deployment model, right? It can run on AKS or even just a container instance as a Docker container. It's a simple API. Right now, there's already a plugin for Nextflow, so you don't have to do too much development. The idea that is we would help develop the backend for Azure. There's already a test API also for Slurm clusters, and there's one that's developed in Europe for Kubernetes. So the idea is that we would not have to hit multiple endpoints. You would just hit the same test API, and then you could do compute on any different endpoint. We have deployment instructions for Azure, which is all open source. We deploy Azure Postgres database. We can run it anywhere. And then we do the distributed compute currently on Azure Batch, but there's nothing stopping us going from a different compute environment in the backend. And then we have additional security that we've done to harden the network infrastructure and security requirements. So effectively, we have this basic architecture where you can deploy this test endpoint in a Kubernetes cluster, and it handles all the responses to Azure Batch, but also Nextflow just talks to the test endpoint. And it provides you with the low cost effective, what's the lowest cost, cheapest machine needed to run your compute, and does all the scaling. So our next steps is to improve documentation and handling, being compliant with PHI level, and we are currently testing and working with engineers within Sakara to do full Nextflow support. Right now it's partial support. There's some gaps, but we're hoping in the next couple of months we'll be able to bridge those gaps. Thank you.
Thank you so much. Always delighted to see GA4GH standards getting featured. All right, a question for you. Can Copilot diagnose or help with cryptic errors during a Nextflow run?
Maybe. This is where we would actually want to work with Sakara to see if we, and the community, to see if we can improve that, right? Right now, it's only trained on code. If we can train it on Slack messages or other options, we can probably get better responses on what those error messages are.
Kind of related as an example of something that people would want to see, can Copilot tell me what to expect the contents of a channel will contain? Because that would be very helpful.
I don't know. We can test it and see if it does. It's a good idea.
That's a good answer.
Yeah.
Thank you. All right.
Thank you.
All right, thank you so much. Now next, Phil Ules is going to give us an update on the Nextflow community.
Stuff. Okay. Thank you very much, everybody, for coming, firstly. It's an absolute pleasure to stand here in front of all of you and be given the task of talking a little bit about our community and what's been going on recently. For any of you who haven't spoken to, my name is Phil Ules. I work at Sakara, and I've been involved with the Nextflow community for a long time and worked with many of you in this room, both with Nextflow and with NF Core. And I'm just kind of going to talk to you today a little bit about a bit of an introduction to Nextflow and NF Core. Maybe some of you in the room are relatively new to the ecosystem, so just a bit of background, touch on a couple of points which I think are sometimes missed. And I'll go through some of the things we've been working on and seeing coming out of the community in the last kind of 12 months or so, and then wrap up with a couple of new things that we're bringing out for you. So Nextflow is, of course, now with our lovely new logo, is a kind of a powerful engine that drives all of this. It's the language and the runtime, which allows you to write your analysis pipeline, run it on pretty much any compute infrastructure, work with any storage. And like any kind of programming language, it's as powerful as the person writing the code. And you can write Nextflow pipelines in any way that you feel, really. And when we started NF Core, it really initiated around this idea of trying to take the incredible flexibility of Nextflow, but constrain it slightly to make it easier for collaboration. And so within NF Core, we love standards, we love rules, we love consistent code formatting, and all those lovely things. And by doing that, we can really bring together hundreds or even thousands of people to work on a single code base. And this is made possible by the power of Nextflow itself, that we can actually all work on the same code base and use that analysis pipeline that's built on so many different diverse infrastructures and so many different types of data. And it's a real testament to the power of the underlying kind of tool. And also the power of this kind of grassroots community, where we are driven mostly by people using the tools. I think, I'm curious, okay, how many people in the room, put your hand up if you are personally involved in writing some Nextflow code? Yeah, so Nextflow is not some kind of software tool that's written by people employed to sell a product. It's written by people who need it. And pipelines are written by users. And that strength of that kind of grassroots community really drives everything we do and makes it such a pleasure to run events like this and see the enthusiasm and see all these ideas come together. So before I did anything to do with software, I'm primarily a scientist, and I love to start with some numbers. So what's the shape of our community? How are we kind of growing over time? We've got well over 700. You can count contributors in different ways, but we have many hundreds now of people writing code and collaborating on NF Core repositories, which is incredible. We have over 8,000 people following us on social media. I'm not sure if Twitter is really the best example to give these days, but it's kind of where we started, at least. So it's our strongest user base across the social channels, which is a huge number. And now over 10,000 people signed up to our Slack organizations, which like, I remember when we hit 100 people and I was floored. So to hit 10,000 people just blows my mind every time I see this number. And this number just keeps going up. I keep thinking to myself, how many bioinformaticians can there be in the world? And my expectations keep kind of getting smashed. So this is just we've got 2 Slack organizations, one for NF Core and one for Nextflow. This is just the NF Core membership. You can see 2 things here. Firstly, you can see when the Twitter API broke all of our stats collection metrics in April. And then also you can see at the end the number of active users jumps. That's partially true. It's also partially that Slack changed their billing policies and how they define what an active user is. But whichever way you read the graph, you can see the main thing here is that we are growing and continuing to grow with no signs of slowing down. And these numbers on the y-axis, the shape of this graph has been the same every time I've given this talk for the past 3 or 4 years, but the numbers on the y-axis just keep on growing. And that's just fantastic to see. And you can dig into this a bit more with the active Slack members, of people who are kind of posting and also logging in to find answers. And again, these numbers are just huge. And when we did our last community training, which is online, anyone who hasn't seen it, we do written training materials which are freely available at training.nextflow.io. And then we do live video tutorials which go out on YouTube. And we handle the questions in real time over Slack. And in March earlier this year, we had over 1,500 people logging into Nextflow, into the NF Core Slack within a single week, which is incredible. So I'm happy to say that the community is looking healthier than it ever has, and all signs are great. And really, the final number for the Nextflow is more than just NF Core, and I think most people in the room will agree with me that if you're writing Nextflow code, you're probably checking the Nextflow docs at least once a day. And so kind of one of our gold metrics for assessing the size of our community is just to look at how many people are looking at the Nextflow docs. And we're reaching up close to 20,000 unique IPs per month at the moment. So this is kind of, I would say, the kind of pretty accurate idea of just how big the Nextflow community is, and it's getting massive. Okay, so next, I actually added these slides in relatively recently off the back of a few conversations I'd had. And it was quite interesting yesterday at the NF Core hackathon that we had just upstairs. We had a beginners table. And what transpired is that really none of the people sat there were beginners, but everyone were bioinformaticians who are maybe new to Nextflow or new to NF Core. And the conversation I had there, which I've had quite a lot of times recently, is about how you can use NF Core. NF Core started by collaborating on pipelines, and that's kind of still the prevailing view, which is that NF Core is a suite of pipelines that you can take off the shelf and run as a resource. And that's true. It is a fantastic resource. But what's changed over the last kind of year, maybe year and a half, with the advent of Nextflow DSL2, is that we can make that code more modular, and by the power, again, of underlying Nextflow tooling, we can then start to collaborate on more levels than just pipelines. And what this means is that you can start to develop your own pipelines with NF Core tooling and NF Core framework. And so we've already kind of heard this mentioned quite a few times this afternoon in earlier talks by Robert, for example, who's developed Vtopia, which is not an NF Core pipeline, but has NF Core modules within it. And so this is kind of a quick schematic to give an idea of what this terminology means. The pipeline is the top level thing. That's the thing you run as an end user. You do Nextflow run pipeline. And you never need to know about any of the rest of it unless you're developing pipelines. But within NF Core, we then have sub-workflows, which are kind of chunks of workflows, basically, and then modules, which are individual tool wrappers. So if you've heard those terms bandied around, this is kind of an idea of what it is that we're talking about here. And coming back to the numbers then, if we look at NF Core, we now have 93 different pipelines, which by itself is a big number, but is a particularly big number when you bear in mind that with NF Core, one of our kind of core guidelines that we started the community with is that we only have one pipeline per data type. So there is one RNA-seq pipeline. And this was kind of the foundation of NF Core, really, was to really force people to collaborate and not have competing pipelines developed by different groups. And so this isn't just 93 pipelines, this is 93 different data types, which is huge. And that covers most data types which are prevalent in genomics today, with new ones being added all the time. And now what we're really starting to see is that as the community grows, we're starting to see other types of data coming in. And NF Core came from genomics, but it's not restricted to genomics. And we're seeing pipelines for doing microscopy image analysis, working with proteomics data. And yeah, I think Evan mentioned we've got a proposal on a new pipelines channel on NF Core this week for an astronomy pipeline, working with data from a Meerkat telescope. We had a talk in Barcelona about material science. So we're starting to sort of see this run over and the tooling, which is obviously applicable to so many different fields. And so it's really exciting to see us kind of moving on to this next phase. So 93 pipelines, and then those sub-workflows I mentioned where kind of chunks of pipelines, it might be something which is commonly done in many genomics pipelines, for example, QC of FASTQ data or something like that. We can now collaborate on that chunk and update it in one place and update all the pipelines using the same sub-workflow. So we have 54, this is probably outdated because we've just had a modules and sub-workflows group at the hackathon who have been adding new ones, so apologies, this is probably a bit higher now. 54-ish sub-workflows. And then the bottom level, the modules for a single kind of tool wrapper, we now have over 1,000, which is amazing. So you really can kind of go in and view on the NF Core website this library of kind of Lego blocks, be it a single brick or a chunk of a wall or a whole house. And you can kind of mix and match according to your needs. And just like the size of the community, the number of pipelines that we're building just keeps on going up. And I'm kind of looking forward to a day which I think will come fairly soon when we break that threshold of 100 different pipelines. And quite interestingly, if you take a fragment of the NF Core template upon which all NF Core pipelines are built, kind of a random comment string or something, you can search GitHub for that just to get a rough feel for how many other people are using the NF Core template to build pipelines that we don't know about, like the dark matter of NF Core, and you get around 1,000 results. And that's just on GitHub. So many, many people building with NF Core, which really makes me very happy because it shows the value that we can bring to the biomedical community, especially. A little bit now about NF Core tools. So we have the template and we've got these components. And what NF Core tools is an additional command line tool, actually written in Python, for working with NF Core pipelines. And again, it can be actually any Nextflow pipeline. And if you do install NF Core on the command line and do NF Core -- help, you'll see a bunch of different subcommands kind of split up according to those which are good for people using Nextflow pipelines and people developing them. Things like listing available pipelines, also launching pipelines, which can be both a command line wizard if you're running offline on a cluster, or it can launch a rich graphical UI. Things for downloading pipelines so that you can transfer them to an offline system. And these commands are really being very heavily used by people in the community. And then in developers, we kind of joke that you can't do anything new in NF Core without creating a new lint test for it. And what this tooling does is kind of helps us to enforce consistency across pipelines. So if we change something, we make sure that the old file is removed. Or if we define a new style or a new standard, then we try and automate as much as we possibly can to ease the maintenance burden. And then there's tooling for creating new pipelines, adding a module to a pipeline, updating modules within a pipeline. And all these things really, really streamline and speed up the pace at which you can build a pipeline and keep it up to date. And what's really important is that these are for everyone, this tooling. Coming back to the same theme, NF Core tooling is for everybody. So if you want to do NF Core download, that should work with any Nextflow pipeline. and it will try and grab the containers and it will download it. If you want to add a module to a pipeline, as long as you follow the NF Core standards, that will add modules to any custom pipeline. And so this tooling is hopefully for the whole Nextflow community. And if you try and it doesn't work, please tell us, because we're doing our best to kind of make it work with everything, even if you're using GitLab instead of GitHub or anything like that. It should still work. And so, without having too hard on this, you can kind of get the picture that you can mix and match, have your own custom pipeline with NF Core components to whatever extent you like, and even have your own custom repository of modules written in the NF Core style, which are purely in-house for collaboration across teams within your company or institute, and mix and match those with modules which are available through the community. Right. Now I'd like to quickly touch on some of the new initiatives and things we've pushed out over the recent months to kind of, from our side, our community team within Sakura, and also from the community itself, which I think are particularly exciting. Something, if you're at a hackathon, you'll have heard mentioned a lot, possibly even worked on directly, is this new framework for testing Nextflow code, which has come out of a group led by Lucas and Sebastian, and it's called NF Test. And this is great because for years, I think probably almost going back to the first Nextflow meeting I ever went to in 2017, there's been discussions about, it'd be great if we could come up with better unit testing for Nextflow code. You know, in the early days, we ran CI testing, which just ran the whole pipelines. We still do that kind of end to end, but it's been difficult to do granular testing. And with the advent of DSL2 and these shared modules, we now had individual kind of building bricks, which we could test one by one. And in NF Core, we've been using PyTest and PyTest workflows to do that. But it's still, we're sort of having to work the tooling around the code. And what NF Test does is it really kind of gives you this custom DSL written in Groovy, very similar to Nextflow. And it gives a much more integrated way and kind of seamless experience for writing tests for Nextflow code to ensure code quality. So this, I think, has been a huge success, this project, since they launched it not that long ago, and has seen a massive uptake. And now within NF Core, we've kind of decided to adopt this and are trying to set up NF tests for every module, all 1,000, every sub-workflow and every pipeline. So if you're building your own pipelines, I recommend checking us out and trying it out. On the Nextflow side, something which kind of we've built into core Nextflow, or Paolo's built into core Nextflow functionality, it's been lurking for a while, but it's starting to kind of really see uptake in the community now, is a kind of a system for having plugins to extend Nextflow functionality. Like any plugin system, the idea basically that is you can write your own plugin Groovy code, compile it, release it, and we have a central location to kind of point to these releases. And then you just define the name of the plugin and the version in a config file, and that functionality will be rolled into the Nextflow runtime when you launch your pipeline. And we're starting to see real uptake of this system now to build in custom additional functionality, which is maybe kind of a bit beyond the borders of the core Nextflow tool itself, and really allows kind of an easier input for custom bespoke code and for community contributions. We've got 3 plugins here which have all come out in the last year or year and a bit. The NF validation plugin, which we built from code which was originally in the NF Core template, and we spun that out into its own plugin, which keep all of the NF Core tooling and template as clean as possible, and now has a lot more functionality. And this plugin can validate parameters that you used as inputs for a pipeline against a supplied Nextflow schema, JSON schema file, to give immediate validation of anything that's been submitted incorrectly. Also does things like generating nice command line help. And goes further than that now. You can also, if you have a JSON schema file for the input sample sheets, there's a new channel factory, so you can just say from sample sheet, and it will generate all the nicely formatted Nextflow channels with meta objects and all this kind of stuff. So it's very quickly become quite a key part of NF Core pipelines, and is a very powerful plugin for anyone else building. NF Prov is for provenance reporting, and really allows you to generate output files along with your Nextflow workflows, which are very, very detailed about exactly which steps ran, what output files were generated. And this is of particular interest to anyone working with, for example, compliance or ISO accreditation, clinical validation, things like this. And that's been, again, driven from requests from the community. And a fun one which was announced at the Barcelona summit is the NF-CO2 footprint, where it's a collaboration with done from Cubic in Germany with Loic in Cambridge, who works on an algorithm to estimate CO2 emissions from energy usage. And because we have all the data about CPUs and memory and time and everything, we can estimate the kind of energy footprint of a given Nextflow run, and hopefully suggest improvements. And hopefully not just make you feel bad about all the tasks that failed and you had to retry. And then two more mentioned from our kind of sponsors here, MemVerge and NFQuilt, both here partners with Sakura, working to build additional functionality into Nextflow for their platforms. And in fact, Ernie is giving a talk tomorrow about NFQuilt, so you can hear more about that there. And if you're interested, please go and chat to them. So it's a really nice entry point into extending Nextflow. This is a slide I added in this morning based on some conversations I had in the Cheeky Monkey last night at the NF Core Hackathon Social. And we were chatting about how many people are starting to use Nextflow pipelines more and more for clinical settings and doing things to do with accreditation, be it with the FDA here in the States or ISO accreditation in Europe. And while no two kind of validations will ever be the same as one another, they do share a lot in common. And so I think there's a lot of appetite for how can we apply this model of collaboration, which we've seen with the code in NF Core and Nextflow, how can we apply a similar kind of idea of collaboration against the actual paperwork that everyone's having to do. So if anyone's interested in this, I'd love to continue this conversation. We've got 2 channels in the NF Core Slack, one called regulatory and one called benchmarking on those 2 topics. And for example, I'd love to put together like a web page pointing to all the known public documents for reference. And maybe even in the future, we could have NF Core modules tagged with any kind of FDA regulations which they've been used in previously to make it easy to build new ones. Some other big projects from the NF Core infrastructure team. This one is close to my heart. The old NF Core pipeline was written by me in a rush in 2018 in PHP and hosted on my personal server. And it sat there for a long time, did remarkably well really, but was starting to creak a little bit. And this year, mostly Matthias Hertenhuber in Sweden has completely rebuilt the NF Core website. And building with modern JavaScript frameworks, and specifically this Astro framework, much more robust. We have some lovely new functionality such as a site-wide search, which makes the documentation way more accessible. And so this has been a huge effort from him and obviously impacts the community a lot and hopefully makes it much easier to contribute to things like documentation. So that's been a big improvement. And then on the tooling, there's some really nice projects we're working on. There's been a lot of work on improving the NF Core download tool. And people building pipelines from the NF Core template often say, it comes with all this stuff that I don't really need. So I run NF Core create, and then I end up sitting there deleting all this code that I don't need. And so something that we have worked on and are continuing to work on is making that template more fine-grained so you can choose up front which bits you need. And if you want, you come out with a very minimal lightweight pipeline, which still is compatible with all of the NF Core tooling, or comes out with all of the bells and whistles that you need to build a fully compliant NF Core pipeline for the community. And a little kind of sub-project of this, which I'm quite excited about, is using a package called Textual in Python, which generates terminal user interfaces, TUIs instead of GUIs. And here you can see this is a demo of a pull request which is currently in development on NF Core Tools branch for building, instead of NF Core create, it's NF Core pipelines create. And you can see this is a much more user-friendly way to create pipelines. And this is hopefully a taste of what the future holds for the developer experience with NF Core. Pipeline creation is the first command we're doing this with, but you can see how this would be immediately applicable for launching pipelines, where you can have validation and help text alongside every single parameter. Also, installing modules, seeing diffs of updates. We could apply this kind of interface to most of the commands within NF Core, and I'm really excited to see where this goes. And I hope that this makes the Nextflow developer experience much more accessible to people in the community. No longer do you have to be quite so worried about using a terminal, hopefully. Something we started, or actually it's kind of been dribbling along with Sakura for a long time. Rob Lalonde started it many years ago, and sort of been taken over a bit by the community team and scaled up over the last year or so, is a podcast which we've been doing dedicated to Nextflow, which we've called Channels. And this kind of goes out in all the usual places, Spotify or Apple Podcasts, we put a video version up on YouTube. And it's kind of fairly niche. We go quite in depth on some topics. But it's kind of basically started with our team where we were having all these really interesting conversations talking about stuff going on in the community, talking with the team developing Nextflow about up and coming features and what was difficult and why different approaches were happening. And I kind of thought I wanted to capture these conversations because they're fascinating. And so we started recording them and calling it a podcast. So it's a pretty kind of relaxed setup. So we've started putting these out every couple of weeks on Mondays and racked up very quickly 24 episodes. And they cover all kinds of topics. You can see the last few listed here. Last two were Geraldine interviewing, well actually I interviewed Geraldine, and then Geraldine interviewing people from the community at the last event, but also then kind of in-depth topics here about live debugging within your editor of Nextflow pipelines. Someone was asking about visualizing what's within a Nextflow channel. There's a way to do this with interactive debuggers now. So we've got an episode about that, and an episode pretty much dedicated to why error messages are difficult to make better, which is a topic close to everybody's heart, and all kinds of things. So if it sounds interesting, have a look and check it out, and you can find all these listed on the NF Core website, on the Nextflow website. Okay, and then I'm running out of time, but I'll touch quickly on a few new initiatives which we've launched just in the last month or so. A big one is the new Nextflow Ambassadors program. This is said at the start, this is very much a grassroots community where we see kind of demand in a bottom-up way. And we saw again and again people in the community running training, giving talks about Nextflow and NF Core, and really kind of going to great efforts to kind of spread the word about Nextflow and advocate for Nextflow in their communities. And so we've started this new program of Nextflow Ambassadors to recognize those people and support them. Be it we have a travel fund for ambassadors to go to events if they're doing things related to Nextflow. I've got a bit about this. We're developing a new set of training, like Train the Trainers, to help people deliver training in their local sites, which we'll make that material available to everybody publicly, but to start off with, we're going to work with the ambassadors to develop it. And of course, there's some exclusive swag, so you get a nice t-shirt and some stickers. And really kind of what we're expecting that ambassadors can do is kind of engage with their local communities. There's the community team in Sakura's 3 or 4 of us, depending on whether I still count. And there's only kind of so much we can do, basically, as we scale. The community gets bigger and bigger, and there's only so many hours in the day. So our hope is that the ambassadors will kind of help us and work together with us to really reach out to all corners of the earth. And we have a webpage up about this on the Nextflow website where you can kind of read more. And basically, so far we've kind of reached out to people who are already doing this stuff. That's kind of the thrust we'll continue to go with, where we know that there's so much community activism already. So if you think this kind of fits you and fits your interests and what you'd like to do, check it out. And you can see the first round of ambassadors, which are basically many of the people from the NF Core community who we already knew were super active, but we'll be reviewing all the applications in a couple of weeks for the next kind of batch. And there's a little handbook which tells you more. Next up is the new community forum. So mentions by a few people is that Slack is great, but it's kind of a black box. You type your random error message into Google and often you don't find a lot. But you load up Slack and you register and you log in and you type it into the Slack search box and you will often find people searching for similar things. And that's fine, but it's not great. And also, as we get to really kind of ridiculous numbers in the community, we start to feel that Slack is struggling slightly to keep up with the volume of messages which we're getting. So we're not going to stop using Slack anytime soon. Everything was going to continue, but a new tool that we're bringing out alongside is a community forum, which runs on Discourse. It's a very popular forum platform. And also, this covers all the different products within Sakura because they overlap so much. Very often there's an issue which is to do with Nextflow, but actually it's to do with Wave. And so by having all of this in one place, we can move things around or tag them and bring people in. And this is all publicly visible without login. So please go and have a look and sign up and post questions there, and hopefully we'll start to get kind of a real momentum behind this new community forum soon. Final announcement is our moderator, you've seen already, and I think probably particularly famous in these parts, and Geraldine, who we're very excited to welcome to Sakura. She started, your first day was in the first day of the Barcelona summit, so we really threw her in the deep end. Got her interviewing people in the community on day 2. So we're really excited that Geraldine's joining the team, formerly working at Broad and literally kind of wrote the book on genomics in the cloud. So yeah, so if you're interested in working with the community, especially, of course, Geraldine lives here in Boston, so a local representative able to pop out and visit you in person and help with training and anything like that. So please do get in touch if there's anything we can do together. Right, with that, I'd be very happy to take any questions.
Thank you, Phil, for this amazing update. This is obviously a lot happening in the community. We're actually out of time for questions, but I believe you're familiar with our Slack. Yeah. All right. So thank you, Phil. Please answer the questions on Slack. And I am delighted to call up to the stage Adam Philippi for real this time. Adam has just been recently named the new director of the new NIH Center for Genomics and Data Sciences Research, which is a bit of a mouthful, and he's taking suggestions for new names, if you like, apparently. So Adam, thank you very much.
Thank you, Geraldine. For the invite, happy to be with you. I hope you knew what you were doing when you invited me, because I'm no longer a developer. And so this won't be really in the weeds on the technical side. The last time I actually wrote any program of interest was probably 2 years ago when I was trying to cheat at Wordle. Raise your hand if you did the similar thing when Wordle came out. Nobody. My family is right, I am weird. Well, anyway, that was a fun exercise. But I don't do much coding anymore. But I did start my career as a software engineer. And so think of this keynote as a software engineer's view or tour through what's new in the human genome. And hopefully, I kind of think the same way that a lot of you think, and maybe you'll get something useful out of this that you didn't see in kind of the popular press when this was announced in 2022. So the first thing kind of has to do with a comment on this idea of genomic data science, which is kind of what NHGRI branded this new center as. And I kind of laugh at that term because it sounds like the same word. Genomics and data to me are like interchangeable, so it's like saying non-bred or like genomics or something like this. Because genomics is inherently a data science. Like DNA is information. Look around you, you're living in the matrix. It's just information everywhere. DNA in all of you, DNA on the carpet, DNA on the walls. It is absolutely everywhere. And just to put it into perspective, each one of you has around 3 trillion nucleated cells. Most of your cells actually don't have a nucleus, your red blood cells, for instance, but 3 trillion left that do, 6 billion bases of DNA in each of them. Each little base pair, if you went in with a ruler and measured it, is 3 angstroms in height. And so you multiply all those numbers together, and it's 4 billion miles of DNA in each one of your bodies, which is enough to stretch from here to Pluto. So have no fear, we will have infinite DNA to compute on with these pipelines forever and ever, because if you then multiply by the 8 billion people on Earth, you get 4.6 million light years of DNA, which goes to the Andromeda galaxy. This is truly astronomical scales of data. So when the Human Genome Project started, they had a much more practical goal of 1 human genome, 1 cell's worth, 6 billion bases. That equates to a meter of DNA. Nonetheless, that 1 meter of DNA took $5 billion to read the first time around. It was launched in 1990, completed in 2003. International effort, ton of money spent, but obviously transformational for this whole field, and we're all reaping the benefits of this early investment in genomics. And it's very apropos that we're at a 20-year anniversary of the conclusion of that project, and here's the final paper out of the Human Genome Project International Consortium, finishing the euchromatic sequence of the human genome. And they were very good about being precise in their language in this abstract. I credit them for that. They said we only finished the euchromatic portion of the genome. And if you read the abstract, they admit there's 300 gaps, and they say that many of these gaps are associated with segmental duplication work with new methods. So that's where we came in 20 years later with this project. But you can understand how the popular press kind of got this wrong. Nobody knows what euchromatin is. I doesn't know what euchromatin is. It's the bit of the genome that has the genes. It's accessible. It's cranking out transcripts. It turns out that's about 90% of the genome. It has had tremendous benefit in genomic medicine over the past 20 years, but there's still that 10% of the so-called heterochromatin and a little fraction of euchromatin that was very repetitive. This is the centromeres and other repetitive bits of the genome that were just excluded. They weren't excluded because they weren't interesting. The centromeres are obviously critical for cell division. The ribosomal rRNA genes that build your ribosomes are in these heterochromatic regions that were left unfinished. So it's like some of the most fundamental parts of the cells were left out in this first reading, and it was a very simple reason. The pieces were too small. So if you're doing a puzzle and it's got a lot of repeats in it, like Waldo here, you're gonna just do the easy, unique parts of the puzzle first, and you're just gonna push the small repetitive bits to the side of the table, deal with it later. That's what happened with the Human Genome Project. The Sanger sequencing at the time was dealing with read lengths of about 500 bases. Then we regressed in the 2000s and went to like 50 base, 100 base pair reads. That was like the dark ages for me as a genome assembly person. But thankfully, we've come back around in the last 10 years to much longer reads. And so the solution to finishing the human genome is a very simple solution. If you're given 3 billion pieces and they're all really tiny, just make the pieces bigger and your job is a lot easier. So we were very happy that around the early 2010s, long read sequencing or single molecule sequencing came on the market with the initial PacBio instruments, and that got us very excited that we would finally have bigger pieces to deal with. And then in about 2015, Oxford Nanopore came on the market. And this was the one that really blew our minds because Nanopore could do ultra-long read sequencing, in some cases getting a single strand of DNA, 1 million base pairs in one pass, read out with an accuracy now approaching 99%. Just like the astronomical scales of the data in your body, the scales of the nanopore I always like to highlight because it boggles my mind too. This is the R10 nanopore, a little washed out on the screen, but the dimensions are there, about 100 angstroms square. If you scale that nanopore up to the size of my fist and similarly scale the DNA, that's like threading 3 kilometers of rope through your fist and reading off all the bases that they go at 400 bases a second. And that's all done with a tremendous amount of magic on the biochemistry side, the biophysics side, and the machine learning side. All of the base calling now for nanopore sequencing is state-of-the-art neural network approaches to actually get those bases read, and they can do it with, like I said, 99% accuracy with the latest R10 chemistry. So in 2018, with these new weapons in hand, Karen Miga and myself launched this telomere to telomere consortium with the goal of using this new tech to finish these last remaining gaps. Karen's expertise is in satellite DNAs, and so I was looking at these gaps saying, gee, we should finish these, and Karen was the one that actually knew what was in those gaps. And so our expertise here was really complementary to come together and finish this. Again, we like our simple solutions. We were just going to sequence the heck out of this one genome. And so Shalise Brooks, who's a tech in the sequencing core at NHGRI, spent literally like 6 months because we had this early GridION instrument. It didn't have great throughput. We ran over 100 flow cells of this, just keeping the machine running around the clock to generate, at the time, an astronomical amount of ONT data, maybe 50x coverage in these very long ONT reads. And so this new tech over the last 20 years allowed us to go from the Human Genome Project in the 1990s, where you had rooms full of sequencers. I think this might be the Sanger, I could be wrong, of these old ABI-style sequencers replaced by one tech and one machine generating the data necessary for this project. And then on the back end, I had the very good fortune of recruiting 2 tremendous postdocs to my lab right at the time we had finished generating this data, Mikko Rautiainen on the left and Sergei Nurk on the right. And they came together with a really great approach to combine the PacBio Hi-Fi data and the Oxford Nanopore ultralong data. We started with a PacBio Hi-Fi assembly graph, which is shown here on the left. Each of the little colored noodles is a piece of DNA. If we zoom in on one of the more complex regions, around the centromere of chromosome 2, you can see that it has this tangled structure, as we would call it. Each of the gray rectangles is a sequence of DNA, but there's edges going between them when we're unsure of kind of the order and orientation of those pieces. And so, for instance, this little node here in the middle is a repeat sequence that's adjacent to these 2 unique sequences. We're not sure in which order we should traverse it, so we just keep all of that information encoded as a graph. The Hi-Fi data alone wasn't able to resolve these complex repeat structures. But using Mikko's GraphAligner software, we were able to take those Oxford Nanopore reads, which in some cases were a megabase or more, shown here in red, and align them to these nodes. And this is just basically dynamic programming, Smith-Waterman style alignment, but done in graph space. And you find those nanopore reads mapping to the graph in a very clear path. And so this now gives you an ordering of those nodes. This top nanopore read says, I should start in this node and then go to this node, and now I have a choice, I should go to this node on the right. And that ordering that's inferred by the nanopore reads basically lets you put a number next to each of these nodes, and then you simply follow the numbers 1, 2, 3, 4, etc., concatenating those sequences as you go, and you take a very tangly, complex structure and linearize it entirely. Absolutely mind-blowing that this worked. I don't think that any of us really thought that we could finish the genome. It seemed like such an unreachable goal, but 2020, the data was just long enough, just accurate enough that it all came together, and it snapped into one piece in the summer of 2020, and we got all of the chromosomes done, and that was the release of the CHM13 T2T reference genome. And so if we compare the essential stats of the genome released in 2003, which was HG35, with CHM13 in 2023, all of the gaps have been closed. But what I also want to highlight is the reduction in cost is nearly like 1 million-fold, which is amazing. And the error rate also got pushed down by 2 orders of magnitude. So from 1 error per 100,000 bases to now 1 error per 10 million bases. And so we've reduced costs by about 1 million-fold, increased the accuracy by 2 orders of magnitude, and that's all thanks to the investment in new and improved sequencing technologies and algorithms over the past 20 years. So a testament to a lot can happen in 20 years. This new reference assembly is much more representative of what a human genome actually looks like. So if you pick any sequence out of this new reference and ask, what's the copy number of this sequence compared to any random human on planet Earth, it's 10-fold more likely that CHM13 is going to represent the correct copy number compared to these older references like even HG38, which is underrepresentative of copy number generally due to collapses of very similar repeats, and also inversion status and so forth is much better in these new genomes. So the title of the talk, what's new? We filled in these gaps. What did we actually find? can be summarized by two words, segdupes and satellites. So segdupe stands for segmental duplications. This is a large chunk of sequence, sometimes multiple megabases in size, that's just basically copy-pasted from one part of the genome to the other and highly identical, say over 95% identical. Satellites are also a repeat, but these are the tandem style repeats where you have maybe 1,000 base pair unit repeated in tandem many, many times, and those tandem arrays make up the centromeres, for instance, and those too can be 5 megabases or more in size. And those segdupes and satellites are highlighted in magenta in this figure on the left, which is showing all of the regions that were filled in with the CHM13 project. And compared to HG38, it is about 8% new sequence, totaling over 200 megabases of sequence. About 3/4 of that sequence are these satellite variety repeats, and about 1/4 of it are the segdupes, which are actually quite gene dense as compared to the satellites, which are free of any gene sequences. But at the bottom, I say an important stat, that compared to HG38, CHM13 has twice the number of bases in segmental duplications that are greater than 95% identity. And so these are very similar repeated sequences through the genome, and as I said, they contain genes and other important sequence. And why this matters is because identity is basically a proxy for evolutionary time. And so because these are highly identical, it means they evolved very recently. They appeared very recently in the genome, and it's precisely these segmental duplications that contain genes that are important for human-specific features, brain development, and so forth, compared to our closest relatives, the great apes. One of the places that is heavily enriched for these regions, as you can see on this plot, are the short arms of the 5 so-called human acrocentric chromosomes. And so this was an area of the genome that we paid particular attention to in the CHM13 paper. And these are known to be functionally relevant because the short arms of these 5 chromosomes are known as the nucleolar organizer regions, and they're responsible for forming the nucleolus, which is a subcomponent of the nucleus. That's basically the factory that cranks out your ribosomes. So here we have this completely essential component of the cell, and the bit that pulls it all together was just completely unknown. The short arms of these chromosomes were just all N in all the prior human references. They're all organized in a very similar way of having a distal satellite region, an rDNA gene array, and these are the RNA genes for the RNA component of the ribosome, and then a proximal satellite region. But in the past, all we could do is look down at the microscope, as we've done here in this fish, and like label the rDNAs, for instance, in pink here. But the exact base for base sequence of all of those short arms was basically unknown. When we finally decoded all of that sequence and looked at what was there, we discovered something that I think is really cool. This is my favorite example from the T2T project and the Pangenome project, kind of discovering new biology. And this was really a discovery that was made in coordination with Eric Garrison, who, if you were in Barcelona, you probably heard about some of this, and Jen Gerten. And what we observed is on these short arms, there are large multiple megabase segmental duplications that are shared between different chromosomes at an identity well above 99%. And so this is sequence on different chromosomes that's as similar as sequence that you would find on 2 haplotypes of a single diploid genome. And that was unusual. We didn't have that in the genome before, and so finding this was a real discovery for us. And the one thing that I want to point out is that, anytime you see sequences that are very similar, I pointed out that that means that they're very related, close in evolutionary time. When you get to like 99.9% and above, we're talking about active recombination in the genome. The reason your haplotypes are so similar is because they're actively recombining via meiosis in the population. And so to find it between 2 different chromosomes was unusual. This led us to the hypothesis that there's actually meiotic recombination happening between different human chromosomes in these spaces, mediated by what we're calling these pseudo-homologous regions. And so these are 2 regions, very identical, between 2 different chromosomes, mispairing during meiosis, getting a crossover event, and in this case of 13 pairing with 21, you're taking the little distal bit of 21, swapping it for the distal bit of 13, and now you have a situation where sequence that was once thought to be maybe unique to chromosome 13 could be found in a different human on a completely different chromosome. And so this kind of breaks a lot of assumptions. A little bit rewriting the textbooks, you learn about homologous recombination. It's always taught the homologs pair, you get the crossover. We know that's not strictly true because X and Y are not homologs. They cross over in the pseudo-autosomal regions. This is kind of analogous to the pseudo-autosomal regions, but on the short arms of the acrocentrics. This led then to a really cool finding that one of those PHRs we found to be inverted on chromosome 14 relative to 13 and 21. And in this case, if you get a mispairing, because that PHR is inverted, you take two of the long euchromatic portions of chromosome 13 and 14 and fuse them together head to head, and you get this fusion chromosome that's called a Robertsonian. And this is the most common fusion event in human genomes, probably more frequent than 1 in 1,000 births. And sometimes I'll be giving talks and people will raise their hand in the audience, I have a Robertsonian. It's generally benign, with the exception increases the risk of trisomies or Down syndrome in your offspring. It was always thought that these fusion events happen at the centromeres or the rDNA arrays, but we're finding now it's these PHRs that are mediating, and it's happening during meiosis with kind of standard crossover recombination. So to really prove this, we're in the process of sequencing some Robertsonian carriers to kind of pinpoint exactly the location of those crossovers and look at the haplotypes surrounding them to show kind of the linkage patterns that would indicate a recent recombination event. So that's the biology story and kind of motivating why it matters to have complete genomes. Robertsonians have been known for decades, but we didn't know how they formed. We complete the genome and just instantly, without expecting to find that, we made this discovery by happenstance. What I want to share with you all, though, is kind of all of the other assumptions that break for people that are building bioinformatic pipelines if you want to analyze these very repetitive regions of the genome. And the biggest problem is that our old friend read mapping just fails completely in these repetitive regions of the genome for a number of regions. And if you want to understand these very recently evolved, highly dynamic regions of the genome, you have to use different approaches. And it really comes down to the idea of reference bias. And so a couple of just very simple examples to show why this happens so we're all on the same page. T to T CHM13 completed gaps. Completing gaps in the reference fixes bias for a very simple reason. If I have a 2-copy gene and one of those genes is absent in my reference and I map a patient to the reference, all of the reads that are originating from that second copy have nowhere to go. They pile up on their homolog, and you get these pile-ups, which are the ugly plateaus in your IGV plots where you get tons of false positive variant calls that basically hides that whole region of the genome from any serious analysis. So obviously, filling in those gaps in CHM13 did a lot to address this type of bias because now the reads can map to the correct location. Here's a real example of that. If you're familiar with IGV plots, this one on the left will give you nightmares. The one on the right looks much better. This is 4 different human genomes aligned to HG38 on the left and aligned to CHM13 on the right over this one pseudogene paralog of the FRG1 gene. There's only 9 of those paralogs in that gene family represented in HG38, when in reality a typical human genome has, say, around 23. All of those extra paralogs just fall on top of the ones that exist in HG38, and you can't call SNPs in this region. But if you align to a complete genome, they go to their correct copies, and you get a much more sane variant pattern. There's a second problem, though, that CHM13 is just a single genome. The copy number between everybody in this room is not equal. These very large gene families tend to vary in copy number between individuals, and gene arrays, where you have the same gene repeated many times, also varies considerably. What I want to point out is that the difference of having gaps in a single reference is really the same as having gaps in the pangenome. If we just have a single reference, we can't address issues where my patient has 2 copies of this gene, the reference only has 1 copy. This manifests kind of exactly like the incomplete reference genome problem. All the reads pile up, you have a problem. You need to map against a reference genome that has the same copy number as the patient that you're analyzing. To kind of highlight a worst case scenario in the human genome that we encountered, we can talk about the TSPY gene array. So this is on the Y chromosome. The Y chromosome is just like a wasteland of genomics if you ever have to analyze it. I'm sorry. There's so many repeats, and there's a lot of reasons why. We can get into it in the coffee break if you're interested. But this is an essential gene for male fertility. It's involved with spermatogenesis. We don't really know what it does. We don't really know any variants in it that have any effect on fertility. And it's because this is what it looks like. Each of these rows is a human haplotype, like an individual assembled Y chromosome. Each of the columns in the little colored boxes is a TSPY gene, a functional gene, and all of the colors are all of the different varieties of the TSPY gene. So think of it as like an allele. And you can see the copy number varies tremendously from about 20 copies to 40 copies. The arrangement of those colors varies considerably. And if you look down at the bottom, HG38 has like, I don't know, 8 copies, and the T to T has 40 copies. So imagine trying to map this individual that has 40 copies onto 8 copies. It's just going to be hopeless. So you simply can't analyze these type of genes with these mapping-based approaches that we've used in the past. There's another even more interesting example on this slide that the far left column and the far right column are TSPY2. And it's a completely separate but related gene, also functional, also protein coding. But in about 80% of the samples, TSPY2 happens downstream of the TSPY array. And in 20% of the samples, it's involved upstream of the TSPY gene array. And there's a big inverted repeat around this array that at some point in the evolutionary history of the Y chromosome, there's been a gene conversion event that moved the functional copy of TSPY2 from upstream to downstream. And so it's not just the copy number that's a problem. It's also that the genes are like moving location, and that if you look at ref-seq annotation or GenCode annotation, TSPY2 genes are only named by like the 8 variants that exist in HG38, and so the naming schemes just get completely broken by these gene arrays. But the TSPY2 is an even different problem, that the gene that you care about actually changed location. And so if you think about that happening in my patient sample, the functional copy is the right-hand one, but I map it to a reference where the right-hand one is the annotated pseudogene, all of those variants are going to be misannotated as in a pseudogene and maybe not relevant when they're just showing up there because they were misaligned. And so this is what the pileup looks like if you take nanopore reads. So you think, oh, long reads, this will solve the problem. But I'm mapping nanopore reads against HG38, which has TSPY2 in a different location. The nanopore reads see all of that surrounding genomic context, and they want to map to that. The gene conversion is just like a few thousand base pairs in the middle that's moved it. The nanopore reads kind of outvote that, and they map them all to the pseudogene in this case. And then you get all of this nasty clipping, all of these false positive variant calls, and everything breaks here, and you can't call variants. And this was brought to our attention by Justin Zook of the Genome in a Bottle team because he was trying to make a variant benchmark for chromosomes X and Y based on our T to T assemblies and realized I can't really make a variant benchmark in this particular gene because we can't map reads to it. And so we've learned a lot of interesting lessons in the T to T project about all of the ways read mapping can go wrong. And the first is that structural variation is rampant and probably underappreciated in the human genome because it's specifically enriched in the segdupes and the satellites, which are specifically the regions of the genome that have been dark to us for the last 20 years. The second point is that those satellites and the gene arrays, by nature of them being in these large tandem arrays, evolve differently and by a different set of rules. Rather than just point mutations and small variants, they undergo unequal crossing over events, which expands and contracts the arrays in large chunks. They can recombine with themselves or other parts of the genome. And so rather than just small variant point mutations accumulating, they do accumulate those, but in addition, they have these very large-scale evolutionary processes. None of the alignment tools model this. All of the alignment tools, if you think of a scoring matrix for a read mapper or what have you, they have probabilities for like insertions and substitutions, and that's it. If you try to align 2 centromeres with Minimap2 or whatever your favorite aligner is, it will just completely fail to do it in a sensible way. And it's because the scoring schemes are not set up to model this type of evolution. Segdupes are also super interesting, and the Eichler lab has dug into these and found that they are undergoing a higher mutational rate of small variants, and they're also, as shouldn't be a surprise, more prone to these gene conversion events by nature of them being so similar. They can recombine with one another in these gene conversions and basically move the functional copy of the gene from one location of the genome to the other. And these segmentally duplicated genes are the ones that are most recently evolved and thought to have an important role in human adaptation. And we know in some cases they're associated with diseases of the type that Evan's lab is interested in, like autism and so forth. And so lastly, because of these weird evolutionary mechanisms, the genes are not always where we think they are. This causes problems when you map long reads. Sometimes you're oblivious to this fact when you map short reads, because they'll happily map to the functional copy and call variants in it without really telling you that the functional copy is now on a different chromosome, for instance. And that location matters, because where the functional copy is determines the regulatory landscape that it's around. And so we want to know where it is in the genome, not just what variants it has. So what's the solution? I don't have a solution for you today. I understand this is a very practically minded conference. And so I can't really say this is how you should all go back and restructure your workflows, but I can kind of give you my vision for where we might be in 10 years. And it's very simply, we all have a unique genome, and we all are our own best reference genome. And when you have a patient come into the clinic, what are you trying to do? You're trying to infer the diploid genome of this individual, and by mapping short reads to a reference, you're just doing a little poor job of assembling that genome. You're getting most of the genes, yes, you're getting 90% of the genome fairly well, but that 10% that Evan and myself and others find most interesting, we just can't do it with read mapping. The flip side of the coin is that, yes, we admit de novo assembly is still costly and requires a lot of expertise. Maybe $10,000 per genome is what we're currently paying for the Human Pangenome Project, with a lot of downstream compute and annotation costs. But I think what we want to do is some in-between of assembly, de novo, and read mapping. Because read mapping is taking advantage of us knowing what a human genome looks like. De novo assembly is basically ignoring all prior information and just saying, just do it from scratch. There must be an in-between. And I credit my former postdoc, Alex Dilthey, I think was the first to coin this term of genome inference in his work with MHC typing. And it's really, I'm looking at these reads, I have a database of other human genomes. Can I infer the complete haplotypes from what I'm looking at, given this prior information about what haplotypes exist in the human population? So think of it as like genome assembly, but with priors. But this presents a chicken and an egg problem, because we need to know what human genomes look like before we can use those priors. And so cue the Pangenome Project, the effort that was launched a few years ago to go out into the population and complete a bunch de novo T-to-T diploid human genomes. And so this is a large consortium, including many centers around the world, primarily organized by University of Santa Cruz, University of Washington, WashU here in the States, but also many others. But what I want to share with you is that it's a very simple idea. If we talk about pangenomes, there's been a tendency in the past 10 years to talk about graph genomes. And that's a very scary concept to clinicians, because they don't know what graphs are. They don't know how to analyze graphs. I don't know how to analyze graphs most of the time. But the pangenome doesn't need to be overcomplicated. And I've been winning this mission of getting people to stop talking about graph genomes and just talk about pangenomes as a set of haplotypes. All of the chromosomes in your body are just linear representations of the genome. No different here. We're building a database of linear haplotypes from the human population. And then we want to show that replacing a single reference haplotype with this collection of diverse haplotypes from ancestries all around the world reduces reference bias to a significant degree. And with the right tooling, it yields immediate improvements to the things that we care about in the common workflows of variant calling, accuracy, and comprehensiveness. And a couple of examples that were highlighted in the draft Human Pangenome reference paper that just came out this summer in Nature, which was a pilot project including about 96 human haplotypes, so a very small representation of diversity, but we still see really nice gains. For instance, a 34% reduction in false positive and false negative small variants when you map with a pangenome-aware mapper like Giraffe. And Giraffe is considering this collection of haplotypes, and it's solving this copy number problem basically and making sure that the reads are mapping to their best haplotype match. They go to the correct gene, and then you project those variants back to the reference genome so you can report it to a clinician in a coordinate system that they're familiar with, like HD38 or even HD19 for that matter. And these precision recall curves are showing this beautiful one over here on the far right is using deep trio as applied to these pan-genome-aware giraffe mappings. Not just small variants, but if we talk about structural variants, you can get twice the number of structural variants called. And both of these results are with short reads, by the way. So you can go back to these large short read cohorts and reanalyze them and get some added gain in terms of accuracy and variance called. There's a really cool tool called PanGenie from Tobias Marshall's lab from University of Düsseldorf, and twice the number of structural variants called when you use PanGenie to infer structural variants. And so kind of like I was just talking about genome inference is actually in the title of the PanGenie paper, which I love. They're looking at the pangenome graph, looking at how the short reads map to that graph, and then basically imputing the SVs that must be there based on what they see. And so that gives you a lot of added power. To just kind of give you a flavor of how that works, and it might work in the future long read space. This isn't something that we have implemented now, but I know that Tobias is working on it very closely. I give you this example. So these are 4 haplotypes taken from the pangenome data set of the Rh blood group antigen locus. And so this is what determines whether you have positive or negative blood. And very simply, if you have this one in the top left with this olive color RHD gene, that's a positive. If you are missing that gene, that's a negative. And then down here on the bottom right, you have people that have 2 copies, so positive, if you will, for this RHD gene. And so obviously this is a medically relevant locus, and it's a nice, clean example of the copy number problem that I described to you earlier, that if your reference is the Rh negative haplotype, and then you're mapping any of these Rh positive genomes to it, no variants will be called in those RHD genes. Or if you have this positive, and you map to the reference that has 1 copy, you're going to have the pileup problem, and again, you won't be able to call variants from it. But what if you rethink it into what I was pitching, that we're all our own best reference, and you look at the pangenome and say, for this locus, what's the best haplotype for my sample? You pull out that haplotype from the collection, map to that, call variants against that, thus solving the copy number problem. And I think it will be much easier to infer these haplotypes than you might think. In the middle is the graph structure as represented in the pangenome, and the colored lines are the haplotype path through the graph. And so this top loop here contains the RHD gene. So all of the haplotypes that go through that top loop are telling you this patient has an RHD gene. This one at the bottom that also goes through this little bump on the side, that's the second copy. That patient has 2 copies of the RHD gene. This path that goes through the bottom skips that altogether. This person has no copies of the RHD gene. Those are the haplotype paths. But now think we have 100 kb nanopore reads. You can map those nanopore reads to the graph. They will have a happy way that they go through this haplotype structure. A lot of this variation is common in the population. You can pull out the haplotype that best matches, and then you have a much easier problem. We've got all the common variation recovered in this inferred genome, and now we just have to add the de novo variants from the reads directly. And you can do that with kind of a traditional mapping and variant calling approach. And so I'm high on these methods to, within the next 5 years, really fundamentally change the way that we analyze these genomes in a way that will dramatically reduce bias, which is a good thing because that means all of your genomes will be equally and as accurately analyzed as everyone else's, regardless of how close a match you are to the HG38 reference. So in 2000, when the Human Genome Project was finished, we were talking about drafted genomes. In 2010, reference genomes became the buzzword. For better or worse, 2020 made T2T genomes the buzzword. I hope in 2030 we just ditch all the prefixes and we're just talking about genomes, and it's your diploid genome at birth that is basically the basis of all analysis. So the future, I hope, is complete genomes as the basis of analysis. It really is just the most natural way to represent things. Why are we representing everything as diffs against one randomly chosen reference when we can just represent the full context? So I've been working on step 1 very diligently in my lab to make the routine assembly of these T2T genomes possible so that we can build this pangenome reference database. I should also credit groups like Hung Lee's that developed the Hi-Fi ASM tool, which has really been the engine of the HPRC over this past year, and that's allowing the construction of these comprehensive pangenome reference databases to form this prior information of what all of this complex sequence looks like in the population. Given all of that prior knowledge, I think that'll help enable these tools that do cheap and routine inference of T to T genomes. One of the nice side effects of this inference idea is that you could probably do it with much lower coverage. Think of it as small variant imputation, where in the 1,000 Genomes Project, you could get away with doing much lower coverage than you would need for a de novo assembly. Maybe you can do very light coverage of nanopore on a genome very cheaply and get an accurate imputation of the full genome. That then gives each of you your own reference genome. Then the question is what's on there and what matters. I would really love to see ML modeling of the language of the genome, the code of the genome, that switches the model. Instead of taking the genome to the annotation, we're going to bring the annotation to the genome. So imagine a magical ML tool that gets a diploid genome and automatically annotates all the gene structures, the enhancers, the promoters, and at the individual base level, variants of concern. I think this is totally feasible with the right training data, right? So that's what I'm hoping to help nucleate in the coming years with the launch of this center and so forth, to build up that training data so that we can build these type of automated annotation models. And that will then ultimately allow you to serve as your own reference genome. And if you think about any health consequences down the line, if a clinician wants to do a functional study on your genome, or they want to do a somatic variation study, or they want to do a CRISPR design, all of that can be matched to your personal genome, and that will guarantee a reduction in bias and a maximum accuracy. So just to end on one practical note, what can you do today with your pipelines that might take advantage of this? Well, you can, as a first step, try out some of these pan-genome aware tools. These are really being developed to serve as kind of a black box solution so that the user doesn't have to worry about the pan-genome. All of that prior knowledge is baked into the tool. And so Giraffe maps to the pan-genome and reports variants, but reports variants relative to HG38, for instance. But it uses the pan-genome in its data structures to reduce the bias. And so you, for instance, can download the pan-genome 96 haplotypes that we have and run Giraffe on it. It's not that much slower than current single reference mappers. In the SV space, I mentioned Pangini as a really cool tool for doing SV inference. Again, those are both short read tools, but we're working very hard on the equivalent long read tools for similar problems. Consider a personalized reference. If you have a very important functional study, imagine that somebody's working on a cell line, they've got an iPSC line, they're differentiating it, they're getting long-read RNA-seq data for it, they're getting a TAC-seq, what have you. Wouldn't it be great if you could just map all of that functional data to a paired reference that you're dealing with? Or in the case of a personalized genome, you're doing a CRISPR design. If somebody's going to CRISPR any part of my genome, I want to make sure that they're screening those CRISPR probes against the 9% that's missing in the current reference and my own personal genome. And so we've had discussions with the Santa Cruz Genome Browser team. They're going to have kind of a pan-genome aware CRISPR screen tool that when you do CRISPR screens, it's not going to just tell you potential off targets against HG38, it'll tell you potential off targets against all of the haplotypes in this pan-genome collection, which is pretty cool. And it's not that expensive. As I said, maybe $10,000 for a single genome if you want one of these paired references for accurate functional, somatic, what have you. And then lastly, as a room full of engineers, be inspired to go develop this next generation of methods with the goal of reducing bias, because at the end of the day, that's what we're trying to do. Make sure that whoever you are, your genome analysis is tailored to you and is not affected by whatever the choice of the reference genome is. And I would love to see these intelligent ML-enabled tools to bring the annotation directly onto the genome so that we don't have to live in kind of this reference-anchored coordinate system. And finally, it's kind of with Robert's presentation in mind, apologies to all the microbial and plant genomics people that have been doing pangenomics for 20 years. This is my secret sauce to human pangenomics, is that I started as a microbial genomics person, and I used to know a PI named Hervé Tedelin very well, and he was the one who coined pangenomics working on strep genomes in the early 2000s. And so we addressed these problems 20 years ago. And if you want to know how it might shake out in the human world, I would encourage you to go look at how the microbial genomics world has handled pangenomics over the past 20 years, and that has some good lessons to be learned. With that, we practice very open science. All of the resources and tools that I mentioned today are available on our lab's GitHub page. The assembler that Miko and Sergey ultimately designed was called Virco. The initial T2T CHM13 project was largely manual. They took all of those lessons learned and shoved it into an automated process called Virco. If you have HiFi and ONT data, it can spit out automatically T2T chromosomes for maybe 3/4 of the human diploid chromosome set. T2T CHM13, obviously available with full genome browsers. We recently finished and released a diploid genome benchmark for HG002, which is a diploid T2T genome that is QV75, and we're trying to get that to be the first basically perfect diploid human reference genome. The Pan-Genome Reference Consortium is aiming to have 700 plus T2T human haplotypes done by the end of the next year. We're currently at about a few hundred. And then lastly, outside of human, we recently finished all of the T2T reference genomes for the great apes plus gibbon, which is going to be a tremendous comparative genomics resource for understanding the complexity and evolution of these very fastly evolving regions of the genome. So I'll end there, and I'm happy to take your questions.
Wow. Thank you for this phenomenal talk. That was very impressive. There's a number of scientific questions that bubble up, a number of technical, practical questions. I have the unenviable job of selecting just the subsets. I
am around for the reception, so
yes.
Feel free to corner me and ask me the hard questions.
I think you might have a lot of customers on that one. I do believe that Venkat is already coding the version of Copilot for ML annotation, so I expect to see a commit very soon. Also, a similar comment/question. Have you started the NF core pipeline for genome inference yet?
We have not. I do not know what Tobias's inference pipelines are coded in. I do have a strong regret that Virco's pipelining system is a bit of a disaster. And so we're going back and re-engineering that in the near future. But unfortunately, no, we don't have a Nextflow pipeline for genome inference yet. That's why it was on my last slide. Please, somebody go do that.
Fair. We might have some volunteers. All right. One question is, so there's definitely short-term, medium, long-term here actions for the community to take. In the very short term, is it worth people switching to the T2T reference, the CH13 reference for their work, or should they wait for like proper pan-genome?
So two answers. The first, which I didn't emphasize well enough, is that the pan-genome contains CHM13, it contains HG002, it contains HG38. So all of these references, including the T2T references, are in the pan-genome. And so if you're using Giraffe or Pangeni against the pan-genome, you're already benefiting from the T2T references, and yes, you will get added gain for that. I think that would be my recommendation over maybe just using a single linear reference, because even though T2T is complete, it's still going to suffer from this representation bias of just being one haplotype. And it's primarily Central European haplotype. The other answer is that if you are interested in understanding the variation within these segdupes, or you're interested in, say, copy number profiling with long reads, then absolutely use the T2T reference. And imagine how much better your copy number profiles are going to be if you're mapping long reads to the T2T reference, and you'll be able to get copy number calling in these segdupes and in these short arms, which are known to kind of have associations and go crazy in cancers and so forth. So copy number calling, analysis of segmental duplications, the T2T CHM13 reference will give you a much better basis to work in than a GAPI HG reference.
Now that makes sense. Now we know that in the community there's a certain amount of inertia around certain tools. Moving people from 37 to 38 took 10 years and it's still not finished. There's certain tools like GTK, that are used all over the place, do not have support for any of this. How do we move people towards the tooling or get the right tooling in the right places so that a wide number of people can really adopt this?
Yeah, and it's really the source of my pitch to kind of bring the annotation to the genome, because it's really like a liftover problem. We have all of this past information, if you think of ENCODE, Nomad, ClinVar, there's all of these tremendous data sets that are basically metadata on top of the genome, and they're all anchored on prior genome releases. And so you need to lift that metadata onto the new references if you want to use them, and that's a bit of a hard and tricky thing to do. And so we need those kind of intelligent tools that do that liftover so well that basically then the coordinate system becomes irrelevant, and it's all that knowledge and the metadata getting correctly lifted onto the genomes that's important. And so I don't think that the solution is going to be that we just lift it all over and then we all use CHM13 and we're happy. Like, I'm looking for the next solution beyond that. The reason that I like the giraffe example in the short read space is because that's all kind of doing this and calling variants, and it's able to project them. Because under the hood, the pangenome is a multi-alignment, and we're trying to infer the orthology relationship between all of the bases and all of the haplotypes. And giraffe is aware of that, and it can try in the VG toolkit to map that back to the reference coordinate system where all of your metadata is located on. So we've tried to lift some of these data sets over, but you lift Nomad over, for instance, and you're only going to lift onto the regions that exist in HT38 because we don't have variants called elsewhere in the genome. So it's a really dicey problem, and it's not going to be solved overnight. And I don't think the solution will be just migrating everybody to CHM13. It's got to be something more complex than that.
Well, thank you very much. I think there's a huge amount of vision there. I'm very excited to see how that plays out. Thank you so much. We are now going to move on to the reception, which will be in the room just up the stairs on your way out. Reception. One quick housekeeping note before we move there is that for breakfast, it's a very important one. Breakfast will be served tomorrow morning at 8:30 a.m. In a room that's upstairs, but we'll have people kind of guiding you when you come in. Just come into the lobby of the hotel and we'll guide you up to the breakfast room. So please join us there. In the meantime, though, we'll have a fabulous time at the reception. And thank you so much to all of our speakers today, and to Adam. Thank you so much.
Thank you.
Oh baby, I wanted you to be